Hope, can you see in full screen mode now?
Yes, sir. Now it is in full screen.
And the slides are moving, correct?
Yes, sir.
Okay, perfect. So I will stop sharing because you wanted to keep some slide in the beginning.
Good evening, everyone. I have some important announcement for all FDP participants. Kindly avoid sending your faculty ID in the chat box. Attendance is not being recorded through chat messages. We are using the Google Meet software system for attendance tracking. Additionally, we request you to fill out the feedback form as part of the session requirements. Your feedback is valuable to us. Please use the chat box only for interactions with the resource person during the session. We appreciate your cooperation in maintaining a smooth and engaging learning experience. Thank you for your understanding and support. John sir, shall we start?
Yes, from my side, I am good to go.
1 second, sir. Let me introduce first. Good evening, everyone. It is with great pleasure that I welcome you all to the second day Adult Faculty Development Program on Strategic Approaches and Emerging Trends in Data Science. Today, we are honored to have with us a distinguished scholar whose contributions to computer science are both profound and inspiring. Please join me in welcoming Dr. John Jose, an associate professor in the Department of Computer Science and Engineering in Indian Institute of Technology, Guwahati. Dr. John Jose completed his PhD at IIT Madras, focusing on computer architecture, and has since established himself as a leading researcher in multi-core computer architecture. His research group, the Multi-Core Architecture and Systems Mars Lab, delves into cutting-edge areas like network on chip, fog computing, non-volatile memory technologies, etc. Dr. John Joe's work has been widely recognized, earning him accolades such as Qualcomm Faculty Award in 2021 and COMSI's Young Achiever Award in 2024. He has contributed extensively to the academic community with over 60 peer-reviewed conference publications and more than 25 journal papers in esteemed IEEE and ACM journals. Beyond his research, Dr. John Jose has been instrumental in various national initiatives, including NPTEL, MOOCs, Spark, JAN, and TWICIP, and he has served as the Vice Chair of IEEE India Council. We are privileged to have Dr. John Jose sharing his insights with us today. His extensive expertise and innovative research will undoubtedly provide us with valuable perspective on the topic Advanced AI in Hardware. Dr. John Jose, on behalf of everyone present, I extend a warm and heartfelt welcome to you, sir. We eagerly looking forward to your session and the knowledge you will impart. Thank you, sir. Welcome you, sir.
Thank you, Dr. Prasad, for the introduction. It is an honor to be called at the FISAT, a program organized at FISAT. Good to see large number of participants coming. So I request you kindly unshare your slide so that I can keep my slide from this end. Yeah. Thank you. Hope you can see my slide.
Yes, sir.
Okay, great. So thank you all of you. First of all, on the outset, let me thank the organizers of this program for giving me an opportunity to come and speak before you on topics that are very near to the research that we do at IIT Guwahati. And then thanks to the central government, especially to AICTE, for granting lot many ATAL FDP programs such that people across physical barriers, location, geographical disadvantages can be updated about recent happenings in the technology field, which obviously, once the faculty is well equipped, it will get translated into students in the classrooms. Since we serve in different board members in different capacities at policy making bodies, including UGC, AICTE, NAC, and in the IIT councils as well, always that has been reflected upon is we need to improve upon the quality of teaching, especially in branches like computer science engineering, the information technology, data science, artificial intelligence, where the number of undergraduate BTech program seats have increased manifold, considering the national level priorities in this field. But the number of quality faculty in this domain has not scaled up the way it is expected to be.
1, 2, 3, 4, 5, 6,
So
7,
this is
8,
a big challenge that we all face at this point. This is a big challenge that we all face at this point. So I'm sure that programs like this, when the faculty members are seriously attending, because once we see numbers more than 200, the general, because we also conduct many programs, and especially when it is online, it is really challenging to catch the attention of the audience, and it's an evening time. It's an exam time for children, where some of you are already parents. So it's a time where fathers and mothers are spending time with their family. So it will be really tough for people also to manage house at the same time attending something technical which will value add. But I promise that this is a very, very emerging area which is of niche importance to Government of India's plan, especially by Ministry of Electronics and IT, which has already a semiconductor plan and wanted India to be a digital giant when it comes to hopefrogging in the field of artificial intelligence. So with this background, let me start. I can take smaller pauses in between, wherein also we give. Dr. Prasad, what is the way in which you handle Q&A? Is it halfway through people chat it, or can you give an idea of how can I interact?
Sir, chat box is available.
Okay, fine. Okay, so I can stop in between also and then ask them to type in chat box, correct?
Yes, sir.
Okay, fine. Thank you. So after this, they have one more session at 7:30.
Yes, sir.
Okay, fine. Okay, so I'll stick on to my time. Thanks once again for those who are joining. I request you to keenly spend the time on this, because these kind of topics are never there in textbooks. Maybe in another 1 or 2 years it may come. And these kind of electives that we offer at the IIT NIT system. So some of you may be already from this system. So these are faculty members who get the benefit of learning these topics. But through programs like ATAL FDP, pan-India wide, people are able to get into these topics. And we look forward for faculty members to come to IITs and join partner research with us through mentoring programs, through internship programs. It's available. We have a lot of internship openings for students, which I will talk at the end of this session. So let me move forward. The topic that I wanted to discuss is about advanced artificial intelligence in hardware systems. So we are already in an era where AI in daily life and AI on hardware is being a lot of talked about. Machine learning and AI is everywhere. We know that right from the Google that we interact, the smartphone that we use, the browsers that we use, the Gmail or any email editor, everything comes with an extension of AI, where lot many of things that would have been manually done by a user, now it has been facilitated with the support of AI in the backend. We know AI has been intruding into the edtech form, wherein AI-based products are available for teaching and learning. AI is available for text editing. AI is available for video processing, for image processing. AI is helping us in security related domain. So everywhere AI has been slowly putting up its hands. It's always a debatable question whether it's good or bad, but then we are sure that AI has improved the quality of life of many of the people, and including the digital gadgets and the digital public infrastructure, which has been slowly building up in developing countries like us. But ultimately, we have to understand anything in artificial intelligence, it's a kind of a program. AI is also a program where the program is trying to mimic artificial neurons. And we know that neurons are the basic unit of any nervous system. So human beings think the purpose of AI when it was first introduced was, can we have a computer program which can mimic a human brain? Since we know that our nervous system consists of neurons, whatever a neuron is been doing, can it be replaced with a set of programs, set of instructions, and then the signals can be replaced with the data. That was the initial way by which AI started. Now we know that AI cannot work on a paper. AI cannot work on concrete. It cannot work on wood. It cannot work on paint. It cannot work on a fabric. Ultimately, any AI-based system, which we are generally aware of AI softwares, AI applications, or programs which make use of AI principle for learning, ultimately, it has to work on a computing system. There has to be a processor, there has to be a computer, or anything that we call it as a computing device, where we are able to work on it. So in short, it has a processor, it has a memory, some peripheral device, and your program, which is an AI program, an AI application, or any program which make use of an AI, ultimately it gets stored in its memory. And from the first principles of the microprocessor codes that we all learned, you have to fetch instructions, decode instruction, and then do. The peculiarity is the impact of execution of this program will be giving a real life experience of how artificial intelligence work. So now, ultimately, we need to understand AI is not only about writing programs or making use of libraries, AI libraries that is available, that is a low-hanging fruit. AI can be done only if there is a powerful hardware at the bottom of the strata. Now, coming to the progress that AI has made over the years, when people talk about AI, computer users or people who are familiar with AI, those who wanted to use AI, we can categorize them into four. The first one of them will make use of AI in their applications. So I am simply a casual user of AI. Somebody wanted to use ChatGPT in making a letter, preparing a slide. Some of you are teachers. You are preparing your course plan, lecture plan using ChatGPT or similar AI models. So already an existing AI is there. We are only merely users of it. That's one. This is the most low-hanging fruit, and it is a most naive application, a common one. It doesn't require a BTech degree or an MTech degree or a faculty qualification to make use of ChatGPT or similar any kind of AI model. Good. The second category is I am developing a software. And now I wanted to integrate some AI tools into it. Let us say I'm developing an enterprise software, a banking software, where I need to have an AI component based upon the face of the user or the customer that is coming into the bank. Automatically his account number has to be opened. So it's a face linking thing. Or any kind of an additional feature. Let us say you wanted to have a Grammarly check. So you are developing a text editor, automatically it should check for Grammarly. So some kind of an AI integration also that has to be come into it. So imagine you have a lock, a smart lock at the door of your house. Previously, it was working with a pin or with a key or with, let's say, an RFID. Now, I wanted to integrate your face recognition model. So once if the owner of the house comes in front of, then once the face is recognized, I wanted to make it open. So what I am using is, I am using an AI model to enhance the capabilities of the product, be it a software or a hardware product that I do. 90% of the case, it's a software product. So you are going to develop a software, you are making use of AI to enhance the productivity, the yield, the quality of service of a software. This is one level above the kind of AI users that I talked first. Now, the third category of AI users are going to be those which develop AI models. So the second model, I use somebody else's model to improve my software. The third one is I am developing a new training model, new testing model, new inference model, which others can use. So you are developing AI libraries, AI packages. It's not an easy job. So someone else can make use of it. So you are actually developing a product. First one, you are using a product. Second one, you are improving the product by making use of an AI. Third one is you are developing an AI product. Now, the fourth category, the most important category, which really rule the world is after AI coming, we know that companies like NVIDIA, companies like Apple, their profit manifold increases because they are coming up with AI chips, AI processors. Ultimately, only these AI processors can give the same performance on applications which are running on AI. Conventional processors will fail. So the fourth category of AI users are those who build computing systems that are useful, that are really needed for AI applications to run. So they make special cloud computers, they make hardwares, they make operating system which is friendly for AI, they make AI friendly hardware. This is the upper class. So people who control that, people who own a cloud, people who own a grid system, people who own a multi-core server, these are the ones who are going to use, because ultimately, if you don't have a real computing power, then even if you have fantastic software, it will not work at all. Now we know that this is a basic diagram that we learn at an undergraduate level computer organization course, where you have a processor and you have a memory, and whatever be the application, be it a sorting program or with finding out a larger number, be it a database program, banking software, whatever be it, it has to be compiled and stored in memory. Similar to that, our current AI application also, it need to be stored in memory. So AI program after compilation is stored in memory. You have an AI model, whatever you call it as model. Ultimately, it has to be stored as a sequence of machine instructions which a processor can understand. So processor will fetch it, decode it, and execute it, and it will operate on the data, fetch the data, and carry out this. Ultimately, it has to work. Let us take an example of a animal recognition program. You have an AI program which will recognize a given image is a cat or not. So the program is compiled and stored in memory. And then when you show one image, this image is stored in memory. I fetch and decode the image recognition program and given an input, that's a cat's image. It has been further subdivided into pixel wise and it is fed into the AI program. Execution of this program will tell that whether the given input image is a cat or not. So we have instruction fetch, decoding instruction, operand fetch, executing, storing result, everything. Conventional computer architecture that we all learned, it is there. Now let me draw your attention to a simple fetch operation. What do you mean by fetching? You have a processor that you see, and then you have a memory also that you have. So this is basically your processor, and this is going to be your memory. And then you are going to run an instruction move R2 from 1000. So 1000 is a memory address. From 1000, I am transferring some contents into register R2. Now, your memory is a slow device and the processor is a fast device. So how much time it will take? Something which operating in microseconds level, a data has to be moved to something which is operating at nanoseconds level. So it is a data movement. What happens when you do this billion times, when you have so much of data to be moved? We already know that different speeds are there for CPU and this memory. So this is a bottleneck. Anything that you move from a slow memory to a fast processor is a bottleneck. When you do it again and again, this is what is known as a von Neumann bottleneck, because we use the concept of stored programs. Anything, be it an AI or a non-AI application, ultimately I need to store this program in memory, and from memory I have to fetch, decode, and execute. This bottleneck is what is known as von Neumann bottleneck. So over the years, people have worked on improving the performance of CPU and at the same time improving the performance of memory as well. So we know that fetching anything from memory is slow. Doing it over and over again, it is going to be a nightmare. So we can already see that there is a hierarchy of data. When we have very slow hard disks, on top of that, we have main memory, then you have cache memories, then you have CPU registers, like this. Now let me draw your attention to another important concept which will make you to understand the challenges in running AI application, something called Turing tariff. So imagine one of the fundamental operation that you need to do with the help of a computer is going to be an add operation. You want to add the contents of two registers. Let me call it as add R1, R2, and R3. So I am adding the contents of two registers R2 and R3, and I'm going to put the result in R1. Now, where am I adding? I'm going to add it in the adder. But I don't know the instruction is added. It is represented as some ones and zeros in memory. When I'm going to bring it, after that, I come to know it is an add instruction. So first I have to fetch the instruction from the instruction cache. It is called memory access. Let's say this process may take 25 picojoules of energy that has been shown. Then I decode the instruction, and then I have to access the registers. Let's say R1, R2, R3 are the registers. I go and take the value, generate appropriate control signals. So the whole process of fetching, decoding, operand fetching, generating control signals, they may roughly take 65 to 68 picojoules of energy. Till now, we have not added. We have made the background ready for two operand values to be added. And the real adding happens in an adder circuit, which may take 1 or 2 nanojoules, picojoules of energy. So overall, the entire adding, let us say if it takes 70 picojoules of energy, out of it 68, up to 68 will be the energy associated with fetching an instruction, decoding an instruction, fetching the operands, and generating the control signals, whereas the real add may be only 1 or 2 picojoules. So let me draw your attention. The actual instruction execution will take, the real add may take very, very few picojoules of energy, whereas the fetch and decode will take lot many energy. Since I see that there are lot many ladies who are attending this program, let me draw your attention to a very common example that will be easy for some of you to correlate. You are involved in a lot of cooking at home. Probably some of the gents also who may like cooking as a hobby may do that. I do enjoy cooking once in a while. So think of a case, you have to prepare a dinner today, and then you may spend 1 or 2 hours, let's say, in washing vegetables and putting whatever is the main course food, and then boiling it, steaming it, making roti or rice, whatever. So the whole process also, and the real cooking maybe, let's say 15-20 minutes. The all other is the background work. Let's say you wanted to make some sabji, and you are going to have the vegetables that is washed, chopped, and then you are putting it inside the gas burner with the oil and then whatever that you wanted to do. So the real cooking is what is called instruction execution, and the others associated with a cooking operation is your fetch and decode. Now, what I wanted to tell is, let's say if someone is coming, the whole cooking and eating will be 15-20 minutes. For that, you have put in 2.5 hours of effort in making sure multiple curries and rice or dal or rice, depending upon whichever part of India you are, whatever is your common dinner that you are going to do. So what I wanted to stress here is Turing tariff means the actual involvement of an operation is very, very tiny, be it in terms of computation time and the energy that you spend compared to the overall overhead involved in executing the instruction. This is called Turing tariff. So we learned about von Neumann bottleneck, which will tell that your memories are slow. So anything that you bring from memory is slow. And at the same time, when you talk about Turing tariff, which will tell the execution of instruction is a very, very small fraction as far as the total operation is concerned. Now, how do you handle it? When you come to specific programs like artificial intelligence, it involves lot of data. Your FDP's name itself consists of data science, data centric. So when you have a lot of data, especially in artificial intelligence related programs, I wanted to operate on this data. Let's say multiply, add, or shift. So since it involves a lot of data, and the moment you talk about data to be multiplied, added, it has von Neumann bottleneck. And this movement will consume more of your energy than the actual process to be done on the data. So how can you think of it? This is something called domain-specific accelerators. Can I think of my underlying computing system to be more specific to the application, more specific to the domain? So can I come with hardware which will accelerate, which will speed up certain application of programs? This is what is called as DSA, domain-specific accelerators. I can go for a hardware-centric approach. I can redesign the architecture, or I can tailor it for domain-specific applications. Some of the applications are heavy applications which involve heavy graphics, applications like neural networks, simulations, performance of heat equations, genomics, coming up with pharmaceutics or medicines for certain class of diseases, predicting something. So, and our focus on today's talk is on neural networks. When neural network is an application, what should be an ideal hardware looks like. I'm sure many of you, since you come for and interested in a data science, then you may be knowing about this. This is something that mimic your human brain. It's an artificial neuron. So artificial neuron is nothing but it is a small unit. It's a small function. The function is supplied with inputs. Inputs can take values, both integer and floating point values. These values are multiplied by another set of fractions, which are called weights. So I multiply the input with the corresponding weight, and then I will get the sum of these products. And then I use an activation function, which is called a bias, and then I'm going to get the output. This is what an artificial neural network does. So what essentially means, think of a case that can I come up with a system where I am fixing the weight and I'm giving the input. If the output is above 0.8, then I say yes, the activity is correct, or whatever input that you have given, it satisfies some condition. Or if the value is less than 0.8, I tell it is not satisfying a condition. Now, think of a case, can I connect multiple such neurons together? This is what is known as a neural network. Okay, so every neuron is connected to a set of inputs, or some neurons are connected to some other neurons of the previous layer. So we have a layer, the first layer, the second layer, then the third layer, like that. We have different layers, and these layers are connected by edges. So when the input value, so you have an image of a cat. I wanted to check whether this is a cat or not. This I will divide into smaller pixels, and this value is now going into this neuron. It will multiply the input value with the weight, and then each of them will do, and the result is being propagating to the next one depending upon the structure. And overall, if you converge it across, let's say 0.7, then so I know if it is a cat, then I have to adjust the weight accordingly. So this is a simple example of, can a computer program mimic whether a given input is going to be cat or not? So it's not like you are directly checking with all cat images. So it's not a pattern recognition at all. So this is what we talked about artificial intelligence. And a collection of such neurons is known as an artificial neural network. I'm sure you are familiar with this process already. Now, what it happens, you have an input that is marked as I1 and I2, and each of this input is going to be multiplied with appropriate weights that I am talking about. So I have a weight matrix, or the process of what I do, what this neuron is doing is multiplying the inputs with weights. I1 is multiplied with the W11, I2 is multiplied with W21, W22 and W23. So you can see that it is a product of two metrics. We have a weight matrix and you have an input column matrix. And then what you see on the right side is what is the operation to be done. So in short, it is actually converting it into a matrix format. And what it does product. I have to multiply one number, which is a weight, which can be a fraction, into another number, which is an input, which can be another fraction. So multiplication of two floating point numbers. Similarly, I have to multiply many such floating point numbers. And once you get these partial products, I need to add them. So in short, this is what is known as multiply and accumulate a matrix. It's a matrix vector product that I'm going to talk about. So a neural network, what you see here, can be represented in matrix, something like this. Some of you may be experts in neural network. For them, consider it as a revision. For others, it may be new. So try to understand it from this picture. Now, what a neural network can do, I can come up with a neural network where, given an input image, ultimately I want to tell whether this image is a Volvo car or not. So you can see, for all the Volvo cars that I give as input, it should always tell, yes, it's a Volvo car. If I give anything other than a Volvo car, then it should tell, no, this is not a Volvo car. So this is something like deep neural network where I have a lot of layers. The layers are connected. Ultimately, the layers need to give you the output that is being required. Now, when you talk about deep neural networks, we have generally two phases in which you make a system ready to work as a deep neural network. The first phase is known as training, and the second phase is known as inference. So what do you mean by training? Ultimately, I am teaching the system. This is a cat. I give another image. I'm telling this is also a cat. I give a third image. This is also a cat. So multiple times I tell the system, because I know what is the output. I am asking the system please adjust your weights in such a way that whenever I give a cat, you have to give output. So I am giving inputs. I know what is expected output, and whenever there is an error, I will correct it. The correction means I will adjust the weight such that for that input, I am going to get output. Now, when I give a new input, for that also, the same weight has to give. So the weights keep on changing. So what do you mean by inference? Once the system is trained, then it is stabilized. Then I am going to apply these weights for a new input value to tell whether its output is predictable or not. So given an image, your inference will tell you with a reasonable confidence whether it's a cat, dog, and all. People might have already worked with this. I'm trying to go deeper into the underlying architecture for it. So what is going to be training? We have a set of input data and we know what the output is, what the desired output is, and we are working again and again unless the weights of the network are stabilized. So since we know the error, I again change the weights, again apply the same input. So now after multiple weight changes for a given image, I got it as a cat. Now I take the second cat image. Again, I am training and I apply the weight changes and I got it as a cat. Now, when I come back with the first image, so now both the first image and second image should recognize it as cat. So like that, when you do not many changes happens, ultimately the system converges with that. That is called a trained neural network. Now the system is already trained. Now I need to move only forward. So it's called inference. Inference, you giving a new input, and since the weight is already stabilized, the system should tell the cat or not a cat. Okay. Yeah, we have someone who raised the hand. Manasai Jayasuriya, you can please unmute and then speak. Manasi Jayasuriya has raised the hand. So if unmuting permission is there, kindly speak.
Yes, unmuting permission is there.
Manasi, you have any doubt or it's an accidental click? Okay. So if there is any query, kindly put up. I will be happy to take up that. Okay, fine. Let me go forward, hoping that people are able to understand up to this level. Now, a simple neural network means we have input and then we have an output and there is a layer in between. When the number of hidden layers increase multiple times or many hidden layers are there, for doing some of the complex tasks, we need to have more number of layers. Then only I may be able to converge upon the result. That is what is known as a deep learning neural network. So when there are more layers, I call it as deep neural network. Now let me try to understand. We are all familiar with the deep neural network that you have here. Now ultimately how you do the computation. We know that all these yellow circles, they are neurons. Neurons will take input multiplied by weight plus bias. So it's a multiply plus accumulator operation that you have to do. Ultimately, who does it? When you write C equal to A plus B, you need an adder and the hardware to perform them. So what you see on the left side is a multi-core processor where we have a collection of processing elements which are capable of performing arithmetic and mathematical functions. Now, my duty is in the operating system is to make sure, let us say this particular neuron that I am talking, where you can see the pointer moving, that activity has to be scheduled here. So the processing element at the bottom left side will mimic the operation of this neuron. And what this neuron does? Inputs and weights. So the input and weight pertaining to this neuron has to reach this processing elements. It has to be multiplied, adding with the bias. And then I have the second neuron will be mapped over here. The third neuron would be mapped over here. Like that, many neurons are mapped for your first layer. The output of those indeed has to be mapped to the second layer. So ultimately, all of this yellow circles has to be scheduled in a processing unit. Now, what does it involve? I need to move the inputs and weights from my memory into these processing elements or this computation unit. So what you see on the left side is a single chip which has 16 processing elements which can perform multiplication, and it need not be sophisticated processes. They are capable of performing MAC operation, multiply and accumulate operations. Okay, so most of the system is dedicated to storing the data and moving data. And you know that output of one neuron is connected to the input of other. Let's say the result produced by this has to be taken all the way such that if this is doing the second layer, I have to get the activity done layer. So this is how typically in hardware it works. So what happens is when you talk about a normal operation versus a neural network operation, neural network, the operation is small. It's not a very complex processing that you do, but this data has to move. The result of one processing element has to be carried over through the underlying communication mechanism to the next processing unit, which is performing the operation. So what do you mean by deep neural network? A deep neural network consists of multiple layers, and I am giving an input. This input is passing through multiple layers, performing convolution, and then ultimately I will converge the value. So in short, these layers are performing convolution operation. Convolution is nothing but met into xi, the function of that, plus b is going to be the bias. So we have input feature maps, and then we have filters, which are nothing but your weight values. And when you multiply the input with the filter, when you convolute in a convolution layer, you obtain the output. Convolutions generally account for more than 90% of the overall computation. It dominates the runtime and energy consumption as well. So this input feature map is multiplied with a convolution vector, different vectors to produce the output feature map. So consider you have three input values. So what I mentioned already is you don't bother about the computation. What you see in the square, the black square is the weight value. I have to multiply the values in the blue with the weight, values in the green with the weight, values in the orange with the weight. And then I go through all these. Ultimately, I will get 1 point as the output. Now, think of a case you have an input vector and I apply a filter. Filter is nothing but the weight that you have. Perform the convolution, and you know what is the operation to be done. This is the operation that has to be done to obtain the final value. Now I slightly move the weight value from left to right. Accordingly, I am getting multiple of these values, what you see now, where the laser pointer is moving. So as the filter move from left to right, the computation also being done, and ultimately I get 1 row of your output value. It's not done. I keep on continue. Now, so far I was moving only on the first row. Now, the first row is completed from top left to top right. Now I move to the next row. There also I perform the operation. Like that, if you move the filter, ultimately I will get this as the output. So from 3 inputs and a weight, which is moving across inputs, I am performing matrix vector product, which is called a convolution operation. And then I am getting an output. This is exactly what happened. 90% of operation of any neural network is this. And if you have a hardware which is friendly in doing this, then my hardware is very much ML friendly, machine learning friendly, or neural network friendly. Let us now try to understand. We are talking about accelerator. Accelerator is a circuit which is specially designed to speed up this. So we have a lot of processing elements which can perform the convolution operation. So what you see, accelerator is a chip. It has some interconnection network through which your input and weight values are reaching the appropriate processing elements. So think of a case that you are going to make, again I use the cooking example. You are all going to make, let's say, a special dish for 100 to 150 people. So these are 8 people who are being assigned. These 8 P's are those which are assigned with the task of cutting the vegetables. So some may be cutting onion, some may be cutting brinjal, like that many people are cutting vegetables. Now there are a set of people whose duty is to make sure that from the vegetable which is collected and washed, I will bring into the room where people are sitting. So one is a vegetable in the market, which is your off-chip memory. You buy the vegetables and then you bring it to the room, and there is a desk where the vegetables are arranged, maybe washed, cleaned, and then you supply to the appropriate person who is going to cut the vegetables. This cutting is your convolution. But what is the duty? You should have a good underlying interconnection mechanism such that the appropriate inputs and weights are being done. So now think of a case, the guy who is cutting the vegetables, the chopped potatoes has to be mixed with brinjal. So maybe he is doing the brinjal and potato mixing. So then the result of one processing element has to travel through interconnection network where he is going to do. So now think of a case, again and again the data has to come. So the supply of data has to be seamless. So from off-chip memory, now consider these vegetables are nothing but your input values and your weights. And the processing elements is where the convolution happens. We have to make sure the data moves. Now come and talk about von Neumann bottleneck. I am going to bring data. Once I perform the operation, then the data is no longer required. Again, bring the new data. So we have von Neumann bottleneck that's been coming. So the actual operation is very simple. I may cut one brinjal, let's say in 5 seconds, but it may take 15 to 20 seconds for the brinjal to be washed and brought it for me. This is called Turing tariff. So I hope you are now able to correlate with the von Neumann bottleneck of bringing something from memory is costly, and the actual operation of cutting or convolution will take very less time compared to the overhead involved in bringing the appropriate data to perform the convolution. So from off-chip memory, I bring it to the global buffer. Then we have something called network on chip, which will communicate the data within the chip, and then it reaches the processing element. So your input feature map and layer parameters or filters and weights will reach there, perform the convolution. Then you create the output feature map, travel through the interconnect, reach back the global buffer, and ultimately it will go back to off-chip memory. Then from there, I am bringing it again in order to process the next layer. So what you see is a seamless movement of this. Over the last few years, many such chips has come to market, which are ML friendly, because if you have a super powerful processor, you cannot be able to perform. It is as good as like we are asking to make it more easy. We are asking, let us say a room consists of people who are all PhD qualified, do excellent research that they are doing. 8 people are sitting. And now the kind of job is only adding 2 plus 3, 2 into 3, 5 into 8. We are giving to these people, they will be able to do. I don't want the room to be filled with highly qualified researchers. Maybe I want these students who are in class 7 or 8 who know addition and multiplication. So how much I need to give them? So when I need to give very high-end salary to somebody who is PhD qualified versus if my room can be arranged with high school students, I can pay them very less, but I have to pay them more number of people. So an accelerator is something, a room filled with high school students than a room filled with 2-3 people or an MTech holders. So my operation is simple operation, but I need to perform lot many of such operation. So this is exactly an accelerator. Whatever conventional microprocessor is, a room consists of a PhD scholar, an MTech student, somebody with a postdoc, teacher, plus industry expert, an IAS officer. That is our conventional processor. Different units have different operation. And now what we talk about an accelerator, ML accelerator means a room consists of high school students who can perform adding, because the operation is adding, but I require many of them. So I hope you understood the difference between a microprocessor and an accelerator. I will take a small pause here. I want the people, whether they are able to understand, I'll be happy to take questions at this point. Any question if you have? If someone is listening at the end, I know there are 309 people, hardly 40 of them will be listening, the others will be busy in their household works. But anybody who wanted to get any answer, it can be a very simple doubt, I don't mind.
No, so we are listening the what are your takings, sir?
So Priya, you are one among the 50 people who listen. I'm talking about the remaining 250. So any doubts in the concept that has been taught? Are you able to understand?
Sir, hello, sir.
We are able to understand whatever you are saying.
Okay. Is the topic new to some of you, or you thought it's a different content would be the topic? Is it interesting?
Sir, good evening, sir.
Yes.
So I'm Srinivasan. My background is management studies,
Yes.
but I can able to understand what you are telling,
Yes.
and the topics are very new to us. But okay,
But you are able
we
to
can
understand,
understand.
right?
Yeah, I can understand, sir. Because your explanations are very simple and it's something simple, sir.
Yeah.
Thank you, sir.
Okay. Great, great. Somebody from engineering background, from computer science, electronics, what is their feedback? Are you able to
Good evening,
understand?
sir.
Please. Yeah.
Sir, actually, I'm from Praveen from RIT. So actually, I have a doubt like accelerators are not standalone. They require support of the microprocessor also.
Yes. So you don't know when you run a program, where is accelerator? Suppose if you wanted to perform a square root cannot be done on an accelerator. So you have a program, you have a main processor connected to that accelerator. So what happens is you have two rooms. One room is filled with all these highly qualified people. The other room is filled with people can do matrix multiplication, simple multiplication. So you don't know in the chip what is the kind of application coming. If the application is coming where you may write a research paper, analyze a result, this people will do. The qualified people will do. When you come to know it's a matrix multiplication, you offload it to the next room accelerator and then do. Hope I clarified that. It coexists along with a microprocessor.
Okay. So the latency involved in giving control to the accelerator, it might be under less than the what is required by the processor to execute.
No. So maybe I'll put it in this way. Okay. Let us say there are, I need to perform, maybe since you all are faculty members, I'll put it this way. The management has 12 lakh rupees in their kitty. Now, the management wanted to recruit faculty members. They have at least, 15 to 20 classes to be handled. So they are asking, should I recruit somebody with a PhD, postdoc qualification and pay them 3 lakhs each so I can hire 4 of them for 12 lakhs? Or should I recruit 12 people and pay them 1 lakh? Should I recruit 24 people and pay them 50,000? Okay. Now, this is effective only if the job that you are doing is mere teaching. So 20 people, each 50,000 will do the purpose of mere lecture teaching. But if it is a high-end job of research, maybe somebody with only a BTech or an MTech background may not be able to do. So what you do is, overall, it should be worth the effort. The amount of operation that you need to do is offloading it to an accelerator, doing it over there and bringing it back is much faster than I alone doing it.
Okay. Thank you, sir. Got it, sir. Thank you.
Any other query from anyone? Great. So let me go forward. So now let me go and more talk about this DNN computation further once again. So what I talked is you have a processor which consists of 16 processing units on the left side, and you have a memory wherein your neural network application is stored. So some inputs and some filters are there with weight value. Now what I do, I first bring the value. So in order to perform a layer operation, first I bring the input feature map, the input values into a processing unit. So I have 16 processing units, one of them through which I get the value. This is a memory interface 1. And then what I do, I know that this particular neural network has 6 layers. So I need to identify 6 such functional units which can perform the operation. So these are the 6 guys. Even though I have 16 of them available in my chip, these 6 guys, which is marked in blue, are the potential place in which a convolution will happen. And then what should I do? I should transfer the input value that is available into all these 6, which will value through will translate into this. Okay. So it's same as once you got the vegetables, looking at the number of vegetables, I need to know, okay, how many people has to be assigned for cutting. So I come up with the number 6. I send the vegetables. Now I have to send up the weight. The weight can be something like your knife. So then I bring the filters. Different types of knives are required. One to remove the bark, peelers, knives, cutting everything. Then I transfer them, the weights also, into the appropriate people. Some require long knives, some require shorter knives, like that. So once you get the input, the vegetables and the knives, then the process is actually cutting. That is your convolution that you do. This will be parallelly done by all of them. And once the result is there, then I have to send back the result into this. So one vegetable is being cut. And then that the cut values are now collected inside this. So this is the process by which from main memory, the data, input and filters are moved. They are assigned to functional units, perform the operation, collect the result back, and then store it back in the memory. Now I give it to the second set of inputs. Excuse me. Second set of inputs and weights. Third set of inputs and weights. Now all these has to be mixed together for further operation. That is my next layer. So this is the way in which things are being moved out. So what is essentially a neural network? We have a specialized hardware with a lot of such functional units. And then when you have a neural network, which has to be done, and this is exactly what is known as neural network accelerator. A hardware which can perform this. Now, when you look deeper into neural network accelerators, it can be of 2 types. One is data flow architecture. Other one is architectures within memory technologies. So data flow architectures can be temporal as well as spatial. And architectures in-memory computing, we call it as non-volatile resistive memories and hybrid queues. Now I'm going to talk about different types of such neural networks. So the first one is known as temporal architecture, which is your conventional CPU and GPU, which has a centralized memory and set of registers, and we have set of ALUs that is available. So from the register, I move the data to ALU, get the result, and put it back into register. So it is like I, as a central memory and register, have the control, and then I assign a value to ALU, get it back. This is called temporal. I use an ALU for the purpose what it is intended to be, and ALU will communicate back to me. ALUs cannot talk each other. The second one, what you see in the right side, is known as spatial architecture, which is also known as data flow architecture, where we use FPGAs, field programmable gate arrays, and ASICs. It has a distributed control over memory. So the memory is now moving into the ALU. The blue portion is memory. In the left side, you can see memory is centralized. Here, every one of them have memory. Every one of them have some control also. So the blue indicates memory, the red indicates control, and the white indicates the processing. And they are connected horizontally and vertically. So the output of one ALU can move to another ALU. Appropriate control signals has to go. And from the main memory hierarchy, you load the value into each of these internal ALUs, which has its own smaller memory, which has its own smaller control unit, and then you do. This is called spatial architecture or data flow architecture. Now, data flow architectures are most suitable for accelerators. Now, we have to understand there are three guys. One is a weight value, other one is an input value, and the third one is now an output value. So we have three types of architectures depending on what if I don't want to move the inputs and weights and output? Can I keep one guy at least stationary? So one is called weight stationary. You keep the weight values in a processing element. So think of a case, you have this processing element which will perform multiplication and addition. That's what is called math. I have put some weight value W0 here, W1, that's a 0.2, 0.5, 0.7. Like that, each of these units will have a weight that is already there. And then we have a global buffer from which the pixel values are being brought into. So when the pixel values are brought, what am I bringing? I am bringing the inputs. Mr. Sudesh, can you please mute yourself? Okay, thank you. So I am bringing the pixel values into these accelerator units, and the weight is there. So anything with the 0.5, I have to go to that unit where 0.5 is stored. So rather than that, I am already having. So think of a case that you have weight. Let's say weight is a different kind of knife that you have. One will be a Malabar knife, the other one is a Cochin knife, like the different types of knives and peelers. So I will make sure if anything has to be peeled off, I have to send it to that guy who has a peeler. So I am not transferring the weights. The weights are already kept there. I only transfer the input. Input is your vegetable. And then I will get the output. So the outputs will move, the inputs will move, but the weights are stationary. Such category of data flow architecture is called weight stationary architectures. Now the next one is the input is fixed. I think only the weights will be moving. So now the blue one is fixed inside. The weights and outputs are only going to move. This is known as input stationary architecture. So imagine that one table already has brinjal, one table already has potato. All what you do is to cut brinjal, I want this kind of a knife, then that kind of a knife is also going. Now the third one is the output stationary. The output I keep it there. Both the inputs and weights are going to move. And that's the way how you are going to do. So it's a data flow architecture. What you keep constant to reduce the data movement, at least one of the three components I fix it. The other component only that is going to move. Now you fairly got an idea what an accelerator is. An accelerator will have a small memory and a small control unit and a MAC unit. That's what you see by a blue, white, and a red combination. Arrange them in rows and columns. We call it as processing element array. And then you have buffers. From off-chip DRAM, I load the value. So IRIS is an accelerator circuit which exactly perform the kind of data flow architectures that we mentioned. There are another architecture like Zimba architecture where you can see the overall system, the chip is like this. Internally that consists of many processing elements, and each processing element internally consists of many MAC units, weight buffers, input buffers, and all. So what I wanted to convey is over the last 4 or 5 years, accelerator chips are dominated the market. Now all the chips that we saw till now it involves a lot of data movement. Data movement is costlier than an ALU operation. So what you can see, you moving anything from DRAM to ALU, let's say it's taking over 200x times compared to moving something from ALU to your MAC units. Moving something from the register file to ALU, maybe take 1 unit. From processing element to ALU, 2x. From a buffer to ALU. So this shows that what is the cost associated with data movement. So data movement is always costly. So any kind of data flow architecture, it is costly. So can I do something? Can I bring in data more closer to place where it is being processed? So this is something called the next category of accelerators, which is called in-memory computing. Can I store storage and processing in the same place? So I trying to reduce the data movement, which will save a lot of my energy. Analog computation, where our dedicated circuit is there. So how do you do that? Let me draw your attention to a new class of circuit, which is called a memristor crossbar. People who are not from computer science background and all, don't worry about it. It's a very simple concept. So what I am trying to do, imagine this is a memristor, which has some property similar to a resistor. When voltage passes through, it will generate a current. Okay, when voltage is flowing through a resistor, it generates a current. When a voltage is passing through a memristor, it generates a current. So it is actually product of voltage into the impedance of the memristor. So, and then what happened? This will produce some current. The next one will produce another current. So what is I1? I1 is typically V1 into G1. V2, that is a voltage which is passed through the G2, the next memristor. So in short, what I am doing, your memristor is storing the weight. And V1, V2, V3 is the input. I1, I2, I3 is the output. So I don't want to make any data movement. Your signal has to simply pass through this circuitry. And ideally, the current that is coming out of it is a representation of voltage into the memristor crossbar's resistance. So this is exactly what you get. So the current is a product of V1 into G1 plus V2 into G2 plus V3 into G3 plus V4 into G4. This is exactly what a MAC unit does. So without movement of data, if you can come up with such a kind of a circuit. So now this is our conventional neural network. If you wanted to go for in-memory computing, I can represent this neural network with the help of, this is the neural network. For example, it has two inputs, V1 and V2. G1 and G2 represents the weight and the cross product of it. So what I get on this line is V1 G1 plus V2 G2. So this hardware circuit, can you come up with a hardware once if the training is done and if you know the weights, then I can keep a memristor of appropriate resistance or the corresponding characteristic, so which can actually mimic a neural network. So when you have neural network like this, I can represent the neural network using an equivalent circuit. So when a neural network in software takes seconds, this will be done in picoseconds. Such fast would be the response of a deep neural network hardware. So what it does is your input is basically a digital signal. I have to convert to analog, then only this. So this whole memristor circuit, memristor array work with analog values. So digital to analog conversion, it will perform the operation and then you convert from analog to digital and get the result back. So it's effectively a weight stationary. Your input is moving as analog voltage. The weights are stationary and you get the output. So this is another chip which is called AICTE, which has a memristor crossbar, which is there in the heart of the circuit. It is called a memristor crossbar array. We can see that, and you have digital to analog converters and an analog to digital converter. So in short, you have a chip where each of this tile consists of some buffers and some IMA and in-memory accelerator. That is what, and each of the IMA you multiply and accumulate. That consists of crossbar, memristor crossbar. Another kind of an architecture is NeuroSIM, which also have a global buffer and tiles, and each the tile consists of multiple processing elements. Each processing element consists of multiple synaptic array. So the process is same. What I wanted to convey is a lot of such accelerator chips are already there in the market. Another popular one is called ZAM. So now what happens, rather than having many processing unit in a single chip, it became architecturally very much a cumbersome process and challenging process to fabricate so many thousands of processing unit in one chip because of wafer restrictions or VLSI technology. So can I have multiple such chips, which we call it as chiplets, and trying to keep all these chiplets under one board? So previously we have a chip consists of multiple processing units. The previous diagram, can you see this is a single chip. which has 4 tiles. Now, what if I want 10,000 tiles? Can I keep 10,000 tiles in a single chip? It became architecturally not possible to fabricate or manufacture such chips. So what will I do? So think of a case. Let us say you wanted to make dosha for 10,000 people. And then what you can go for a burner with multiple, let's say, multiple cooktops, the 4 of them. So you can make 4 tawas. Maximum you can do 4. Maybe I can add up 5. There is a restriction in which the number of burner that is possible in a cooktop. Let us say you can have a specialized one, 10 that is been doing. Still, I want at least 50 such places where I can make doshas. So what I do, I will make these units of 10. So 10 is the maximum manufacturing capacity of a cooktop. I make units of 10 and I connected them, all of them, with the single gas supply. So each one is known as a chip, and a collection of that is called chiplet. So this is what I am now going to show. Each one of them can be considered similar to your cooktop. So cooktop 1, 2, 3, and each may have 5 burners. That's what exactly that you see. And each may internally have multiple crossbars. So this is a CIAM architecture. So the communication between the tile is called network on chip. The communication between packages is known as network of package. Now, so far what we were interested is, given a neural network, how do I do it? What is a kind of hardware in order to facilitate movement? Now, the future challenges are, we are talking about multiple neural networks going to run on a single hardware. For example, let us say I wanted to have an artificial neural network program which will recognize a speech and a keyword. So there are 2 neural networks, one which will recognize a keyword, and then from the keyword I have to understand what the word is. So keyword detection followed by speech recognition. Similarly, I have another neural network which will have hand detection followed by hand tracking, eye segmentation followed by eye tracking. So multiple neural network has to come together. What you see on the right side, hand tracking, eye segmentation, gaze estimation, keyword detection, speech recognition. These are all neural network used for interaction. Then context understanding, segmentation, semantics, object detection, action segmentation, many such things. Word locking, depth estimation, depth refinement, plane detection, like that. So this is something called multitask, multi-model. Once you have multiple tasks has to be done and they have to work together, they have to work in real time, quick. So what is the quality of service when you have such kind of a system? So this multitask, multi-model, that means multiple neural network work on a same hardware. It can be of 2 types. One is a cascade model. That means you run one neural network. Once it is complete, you give the output to the second neural network. So the face detection neural network will make use of the entire hardware. Once face detection is done, then the face recognition hardware will work. Okay, so you can perform locking or unlocking of this. The other model is concurrent. In my application, I don't want one after another. I want both of them should be working together. Then only my application will help. For example, I wanted to put a camera in front of my car for a driverless car. So the driver, or maybe a robot, think of a case. The robot has to, semantic segmentation and obstacle detection cannot happen one after another. I have to work both of them together. That is my navigation system. So sometimes both the neural network, 2 or 3 neural networks work together. We call it as concurrent. Other one is cascade. When one neural network works, the output of that works in the other one. So we have cascaded neural network and concurrent neural networks. Now let me come to the point of this. Okay. So let me put your attention to this. I have 4 neural networks to be running together, which are represented by your green color, your violet color, the blue color, and the orange color. Now I have total 16 units which are capable of doing 16 larger chiplets. Now how do I divide this 4 into the 16? So imagine there is a father who has 4 sons. He has 16 acres of land. How do you divide it across? Some son having a government job, some are teachers like you, good salary that you are getting, some are not learned. So a father may have multiple criteria, the complexity of the algorithm that is running on the father's head in dividing the property. So this model, what you see is temporal multitasking. Is father is telling, all my 16 acres of land is for all 4 of my sons. Whenever you want to use here, one can use. After some time, it can be given to the second one. So I will divide this one to all of them. There is no partition for that. It is called temporal multitasking. In the month of January, the orange guy may be using this. In the month of February, the blue guy may be using the house or the farmland or whatever. What you see on the right side is known as spatial multitasking. So here I understood the orange guy requires more of the space. So out of the 16 acre of land, 6 of the acres is given to the orange guy. 1 is given to the green, 3 is given to the violet, and 3 is given to blue. So it's a fixed partition that is given. So blue has to manage all his operation in the available 3 to them. This is called spatial multitasking. So I am dividing the entire available resource into them. So this is something similar. For example, you have a cooktop with 16 burners, and then you have to make dosha, you have to make sambar, you have to make some chutney, and at the same time you may have to make some rice. So how many of the cooktops you use for making dosha? So if I don't have any partition, I can use anything for anything depending on the need. That is called temporal multitasking. I know that lot many doshas has to be made. So 60 out of the 69, if I go for exclusively for making dosha, so I am using 9 tawas and then 3 exclusively for making sabjis, 3 for sambar, 1 for rice. This is called spatial multitasking. Now we know that in our cooktops, some of them have larger burner, which is used for keeping big vessels, and some are used for smaller one, let us say boiling something. So this is something called, you have big burners and smaller burners, big chiplet and little chiplets. So some may have, the big chiplet may have 200 processing units or 200 membristors. The small may have only 100 membristors. So it's a question of 100 into 8, total 800. This can be 200 into 6, total 600. So it's like resources with different capability. We call it as big little chiplets. Now the question is, we have a multi-model, multiple neural network. Each has its own number of layers and inputs, and which I will map to big chiplet, which I will map to little chiplet. So it's all in-memory computing. How are you going to divide the big chiplet and triple chiplet? So the optimized in-memory computing design for multitask, multi-model means you have to provide an optimized IMC architecture. IMC stands for in-memory computing. Your memristor-based design. Optimize the design based on number of networks, size of networks, and intercommunication between the networks. What are the challenges? How do you group the chiplets? What is the size of the network versus the chiplet count in each of them? What is the optimal input data flow? So in short, what we wanted to understand from today's session is data is very important when it comes to AI and ML applications. We need to handle the data well. Ensure the data does not overwhelm the components. How can you do that? By coming up with intelligent algorithms. If you are good in data structure algorithm programming, contribute to handling data using algorithms. If you are a hardware person, contribute through intelligent architecture. If you like both of them, come with a whole system design, algorithm, architecture devices. So what are called data-centric architectures? Process the data where it resides. Processing in memory and near memory. Now we saw that in the memory itself, we can perform computation. So the weight itself is being represented as a memristor value. And I don't like all this, but I am very much passionate about memory technologies. So because all these accelerators, new generation ML accelerators requires low latency, low energy data access. Can I come with low latency memory, low energy memory? Now I need to store a lot much of data. I need to process them. So high capacity memory at low cost, hybrid memory, compression, intelligent data management. These are all fantastic problems that is associated, and not many industries are looking forward for children who have done a project in these domains. We need intelligent controllers which can handle robustness, and then the security of the data that is been moving. If someone is mal-tampering the data, then the neural network can give wrong result. What's the cost associated? What's the scaling associated? So please do understand, machine learning applications will dominate future computing systems, that's for sure. Effective leverage of AI and ML is possible only with an ML-friendly hardware. So unless the hardware is not reinventing itself, AI and ML will not flourish well. So there is a huge demand in the global community, in the consumer electronics, to come up with more hardware which is friendly with ML, hardware which is compatible to ML. For that, newer chips has to come. And we know that the 70% of the chips are coming from a small country called Taiwan, with a lot of semiconductor factories there. Even though we do design everything, ultimately fabrication come from either from Finland or then now China also started up, because the cost of producing in Taiwan is much lower. Technology is good. When you try to produce the same chip in US, cost will go high. That's exactly what Mr. Trump, the president of US, has been telling. He wanted to bring this job back to US, and India understood during COVID time. Lot many of small chips in our automotives, in our consumer electronics, in our washing machine, in our microwave, any chip, the chip has to come from this China or Taiwan or very limited countries. So even though we have a lot of assembling, we don't have chip manufacturing. And the government of India realized in the last few years, it's not only about writing softwares, it's good unless we don't have computing system which can gather this together. India's rise to super digital power is impossible. So there was a semiconductor policy that was defined by the government. Whatever I told, there is no electronics inside it. Semiconductor is not connected to electronics. People who can write algorithms, people who can write good programs, these are all required because we use a lot of electronic design automation tools. So I don't go and touch transistor. All I wanted is write a program, you will translate, and then the hardware is being generated with that. So in Assam, in Guwahati, semiconductor plant by Tata Electronics is set up. In another 1 year, the chips will start getting manufactured from here. Similarly, to Gujarat, there are 2 plants. Many other state governments like Odisha, Karnataka, Andhra, then Haryana, UP, these are all coming up with land and then trying to attract investors. You maybe see global this investment meet in many of the states are happening in the month of February. It's all in order to attract industries because India can develop make in India, real make in India. So the industries has come forward. Now what happens once the industry has been set up, this industry require quality manpower who can appreciate systems building. So unless from our engineering colleges, we are not having enough people who are capable or worked in projects or teachers who are updated about these technologies, which will translate into student projects or electives, then what happens is ultimately in the same factories, we don't have skilled manpower from India. We will have to hire people from China or from other countries. So even though the factory is here, the employees will be working from other. Since we have a very competitive China as one of our neighbor where you get cheap labor. So it's very, very difficult. So we as faculty members have a huge responsibility in growing with the AI ML wave, or a simple program writing, everything AI will replace, but AI cannot develop chips. Chips manufacturing will happen only through precision technologies, and that will not get easily replaced with AI, at least in the next 1 decade. So AI engines and ML processors will rule the future world, and India need to scale up manpower with passion and skill to contribute to building compute systems that augment AI growth. So this is the way in which I wanted to tell, but then please do understand our higher education system. We have 23 IITs, 31 NITs, many good private deemed universities which are ranked very well in terms of research and placement capability of students. Somehow at our undergraduate engineering education, our students are having a feeling as getting placed at the end of BTech is considered to be the golden motto. So people are thinking about what is a salary package. I always tell there is a Lakshmi Saraswati conflict. Our young generation is focused more on the Lakshmi aspect. You have to keep on working every day. So you know that a maid working at our home work from morning 9 to evening 5. You also work from morning 9 to evening 5. But the salary that she gets or he gets versus the salary that a teacher gets, an engineer gets, an IAS officer gets is different. So the salary is not based upon number of working hours. The salary is based upon what kind of work that you do, how much of intellect that is being required. So for people to understand, we need to prompt them more to the Saraswati. As much as they learn, pick up the right skills. So once they chase Saraswati, Lakshmi will automatically follow. I'm sure that teachers would be able to understand this. So, or else every day they have to chase Lakshmi. After 2 days, if their skill is not good, then there is no Lakshmi that has been coming up. Consider the case of the maid who works in your home. 5 days not coming, you are not going to give salary because it is wages. Whereas you are getting a salary, you have leaves that is available. But for high-end jobs, R&D jobs, if our students are not getting updated themselves, then future is going to be little bleak for us. And maybe, I don't know whether real classroom teaching will be there after 10 years. It can be completely overtaken by AI. So teachers who can add value to the students, who are up to date about what is happening and who can translate them into projects. It's not about teacher learning and showing the slide. Start working on it. It's a very, very competitive field. We are talking about a future where the concept of classroom teaching itself may not come. We can buy, and every college can buy a robot, and robot can be programmed into teaching data structures. Next button, teaching computer organization. Next button, teaching DSP. It is not that far. Okay. So that's all what I wanted to convey. I'll be very happy to take up questions if anyone has. We do have a lot of options for faculty members to collaborate with us in terms of internships. We will be very happy to associate if any skilled training is required in your colleges via on-campus workshops. We don't believe in the concept of IITs only as a tower of excellence, but we wanted to make it as a network of excellence by clubbing up with students, because we know not many teachers in many colleges, in state government colleges, private colleges, are very much talented. Just because of one situation or other, family circumstances, some of you might not have landed in IIT as a student or a faculty. We never undermine the talent of teachers like you. It is a collective responsibility of the teaching community of the country in making sure that the aspirations of a Vikshit Bharat is possible only if the trained manpower come out from our technical institutions, where companies will queue up for hiring. So if you can value add to transforming the mind of a student from an average mediocre BTech or an MTech degree into someone who can marketize themselves, someone who is a treasure of knowledge, someone who is very confident in the subject, and that's what India really wants. So I sincerely request all of you to understand the bigger role that you all play in the respective institutions. And with this FDP, everything is funded with the taxpayers' money. So ultimately, we are responsible back to the taxpayers. I'm sure that at least a bunch of you will understand the sensitivity of the issue and make our students Saraswati chasers than Lakshmi chasers. Thank you.
Have any questions? Participants, please do this time as the discussion.
Please do write to me if at all you wanted to have collaborations or possibilities of the associations, how it is done and all. It may not be immediately possible to absorb everyone, but if someone put an effort to write an email to me, how was the session, what was you liking, and in what way you wanted to grow, either in this subject or other subjects, that are there. Hope it was a useful session, but I'll be very happy if some of you could reflect upon how it was, what is the doubt. Please share. So any faculty wanted to speak up by unmuting?
Good evening, John, sir.
Yes, good evening.
Sir,
Can you please introduce yourself?
Myself, Agil Chandran, from College of Engineering, Talasheri.
Okay, so we met before, 10 years before.
Yeah.
Happy to see you, Akhil.
Okay, thank you, sir. Nice to meet you also. So, sir, I have a doubt about this memristor. Actually, is it a non-volatile type memory thing?
Yes, memristor is a kind of a non-volatile memory. Once it is programmed, it will never go. So you are trying to fix the property of memristor one time. It is not reprogrammable. So it's a fixed weight.
Okay. Sir, I would like to get some your opinion about this DeepSeek and what they develop a large language model that could perform or outperform ChatGPT by claiming that less computing power. So, what is your opinion about using less NVIDIA chips or something like that for computing?
What I wanted to tell is, thank you, Akhil, for the question. Is see, when you were thinking that anybody who is telling somebody comes up with a cooking burner with a lower flame consumption, anything that consume less electricity will be very much attractive. So what happened is, over the years, technology of accelerator was denied to China. So that gave them an opportunity to invest on coming up with AI models which will consume less power. So it is even a better technology by which these algorithms can even be run in a faster way, quicker way, consuming less number of functional units. So once they were, so it is basically the necessity is the mother of invention. So US were deploying on the available chips and China really worked on what is the bare minimum requirement and develop chips for that. So first what happened in US, you have chips, you run AI on it. China, what they did, you understood what is a computing requirement, develop chips bare enough to do that. So drastically the power has come down, and unless someone else is going to come up with a counter solution, their products are going to rule the world. Because ultimately power matters. We need a mobile phone that can save battery. So if an accelerator work in your mobile phone, by evening, what happens? The battery is gone. So we want our mobile phones to last longer battery. So that's a challenge.
Okay, thank you, sir.
So, hello.
Yes.
So, I'm Praveen from RIT, Kottayam. So
Yes.
actually, it was a wonderful session. Actually, I have a question. Like you have mentioned, like both it's a term is in memory. So all these models are for neural networks which have already been trained.
Yes.
Or so what about the training aspect? Because during the training we might be consuming more aspects. So is there any
Yeah.
accelerators especially
So
for
the
training?
systems, some accelerators are good for training. Some accelerators are good for testing, the inference. So we don't try to, so normally what happens in 99% of cases, the training and testing is not done in one place. You have a product, future products are already pre-trained. You have a trained model that has been coming and that you are going to use it. So once if you know the trained, if it is trained already, then you know the weights, then you can pre-configure. So the training and testing, which is just 2 modules in our AI syllabus, ultimately it will become 2 parts when it comes to implementation. Very rare applications of both training and testing together.
Okay,
So you
thank you,
require
sir.
dedicated hardware for training and a hardware with different properties for testing.
Thank you, sir.
Sir, how can evaluate the performance of IO devices when connected with this processor while doing the AI?
So certain AI task requires a lot of runtime input that has been coming. So the bandwidth from IO devices coming to processors is a problem. So ultimately what you look at quality of service. Quality of service as far as an end user is concerned. How much time it will take to recognize your face to tell it is John or it is Siren. Okay. So ultimately, when you have so now you run only one neural network. Future would be 10 or 15 neural network running. So can I quickly deliver the output? Let's say some of you might have traveled to Digi Yatra or the gates open once your face recognizes. That has to be done in 1 second. What if the gate will open only after 10 seconds? Then there is a queue that is getting formed. So our future tickets in railway, in bus, everything is going to be face recognition system linked to Aadhaar. So the moment you show the face, the ticket is being generated or it has been there like that. So everywhere when AI coming, the runtime input, the IO from the camera, from the network are going to be more crucial. And that time we require high bandwidth IO devices, wireless devices, and more spectrum in the electromagnetic spectrum signals has to be used. So equally electronics field and sensor field also has to grow. Ideally, it has to be measured by throughput. So throughput is the parameter.
Sir, may I ask you one doubt?
Oh, yes. Can you introduce you? From where are you?
Sir, my name is Jimmy George. I am from the Vishwajyoti College of Engineering and Technology, Varkulam. I have a doubt.
Yes.
Okay. So nowadays, you might have heard that we have a AI first paradigm. So what is this paradigm and how could it be implemented in the software development lifecycle so that what do you say, the development could be made much more easier and more futuristic?
Okay.
Over to
I
you,
am
sir.
not an expert in the field of AI. I am more expert in the field of systems. But typical generation of what I understand is typical generation of writing a simple program. It doesn't require human intervention. You can generate programs by just giving the context of it. So basic software writing job itself would be easily replaced by AI. So AI first means anything which people have already done in the past, it can be done with the help of AI, but good training. Only the research, when you come out with new inputs, new ideas, which is not done by anyone else, AI cannot do. AI cannot do research by itself because AI requires a training. So that is the area maybe future AI will pick up, but currently many low-hanging programs will be AI generated. That is what my understanding is.
Okay, sir.
So I think it is reaching 7:30. The next speaker may be ready. So if anyone wanted to further write to me, please feel my email ID is already shared. You can go to know more about the work that we do from my webpage. So once again, thank you to Dr. Prasad and team at Federal Institute of Science and Technology for giving me an opportunity to interact with this wide range of audience. From the name, I can understand people are spanning from across different states. Thank you.
Thank you, sir. We are extremely privileged to have you as the resource person for a session of this FDP. We thank you for the information stacked lecture and for providing a deep insight into AI in hardware. Once again, on behalf of Department of CSE, FISAT, I extend a heartfelt gratitude to Dr. John Joss, Associate Professor, IIT Guwahati. Thank you so much, sir. Without any further delay, let's move on to the next session to be led by Dr. Bindu Krishnan from IBM Kochi. She will be continuing the session she had handled in the previous day. With all due respect, I invite you, ma'am, to engage the lecture on classification regression algorithms in Python. Welcome, ma'am. Bindu, ma'am, please.
Good evening. Once again, came back. So yesterday we discussed about the basics of machine learning, especially the role of probability and statistics in machine learning, and including the types of machine learning. So today I'll be focusing on, as Dr. Irene mentioned, I'll be focusing on classification and regression. I don't think with this 1.5 hours, you'll be able to do the practical session, hands-on session with me. But anyway, I'll explain with the programming also. First, let me start with what is this regression classification, what all techniques are there in the regression classification. So I'll show you a manual example. Then I'll show you the programming also with explanation. Okay, let me share the screen. I think the screen is visible, right?
No, miss.
No?
No.
Yes, ma'am.
Yeah, I opened the PPT also. Is it visible to all of you?
Yeah, ma'am, it's visible.
Okay. So yesterday I covered this part of what is machine learning, then machine learning model, then some examples, applications, then what is the difference between AI, ML, deep learning, then especially the role of yesterday's session actually focused on the role of probability and statistics in machine learning. Then types of machine learning, what is supervised, what is unsupervised, what is the difference between classification and regression. Then I showed you some practical examples with that. Then unsupervised learning, clustering, all these things, actually reinforcement learning with an example. So a lot of machine learning algorithms are there, 100+ machine learning algorithms are there. So out of this, of course, today we focus on some of these algorithms. I'm not committing, I can cover, or I'll be able to cover all the algorithms. So with this 1.5 hours, what all algorithm which I'm able to cover. So anyway, I'll give you the idea of the concept behind most of these algorithms. Okay, so simply especially the supervised learning, actually the steps involved in the various classification as well as regression models under supervised learning is we start with a training data set, then learning algorithms, so as to come up with a model, which we call it as machine learning model. Then we need to test that data or test that model using another data set. Finally, we'll reach the output. Of course, we need to measure the performance or assess the performance of that obtained model. So machine learns the things from training data set and then apply the knowledge to the test data set. Okay, now classification and regression. The difference between these two things already I mentioned. One simple example, say for example, if a student, if we want to predict whether a student will pass or fail in an examination, pass or fail, two categories, two classes. So definitely we choose some classification algorithm because these are categories. But instead of that, if we want to verify or if we want to find the percentage obtained by a student, or students, definitely it's a numerical quantity, it's a continuous value. We approach the regression algorithm. And one other example, simple temperature. Yesterday also I mentioned about this. If we want to predict the temperature, tomorrow's temperature, definitely it's a value, it's a numerical quantity. So we approach regression algorithms. Any of the regression algorithms. I'm not saying that regression algorithm is only a single method. No, no, no. I'll come to that. Even in this list, actually, yesterday itself, I shared that what all classification models are here, what all models comes under regression, like that. Okay. So if you want to predict the tomorrow's temperature, it's a numerical quantity, it's a continuous value, definitely we use regression. But instead of that, if we want to predict whether the temperature is hot or cold, then we can use any of the classification method because there it's a category. Okay. Yeah, start with regression. Of course, from that word itself, it is very much clear that linear regression, it's a regression technique. Okay, linear regression. Of course, it is a from the machine learning perspective, it is a machine learning algorithm based on supervised learning. But from the statistical perspective, it is a statistical method to model the relationship between dependent and independent variables, or we can say target and predictor variables. So of course, yesterday also I shared that linear regression is not a new thing. It's more than a century-old method from the field of statistics, which is used for fitting a line or a plane to real value data. Fitting a line in the sense, of course, linear means fitting a line. So other case, a plane to a real value data. So from the machine learning perspective, of course, we look it as a system for learning the weights or coefficients in response to the examples from a domain. But in statistics, regression is method of modeling a target value or dependent target value based on some independent or predicted variables. So anyway, here actually I'm planning to proceed with the machine learning perspective itself. That is, linear regression is a machine learning algorithm based on supervised learning. So it's simply a linear method. Simply a linear method to model the relationship between variables, independent variable and dependent variable. Now, in case of scatter plot, just for example, in case of scatter plot with some points on it, what do we mean by scatter plot? Yeah, this is a scatter plot. So if we have two variables only, take one variable along x-axis, other variable along y-axis. So you will get a set of points. This itself, we call it as scatter plot. So sometimes this plot may get some shape, may resemble some shape. Say, for example, if the scatter plot appears like this, then this means that when x increases, y also increases. That is, there is a positive relation between the variables. Or we say there is a positive correlation between the variables. Because when y increases, when x increases, y also increases. Right? So here actually a positive correlation. But look at this figure. Here actually it is decreasing. When x increases, y actually decreasing. So here we call it as negative correlation. Just inverse correlation or negative correlation. And this is obtained, this correlation actually we have found out using the graph only. Same thing, it is possible to find using an expression or using a type of correlation which we call it as Pearson's correlation coefficient. Yesterday I showed that expression for Pearson's correlation coefficient, that is covariance xy divided by standard deviation of x into standard deviation of y, if x and y are any two variables. So that correlation lies between -1 and +1. So if the correlation is positive, you will get a value between 0 and 1 for that Pearson's correlation coefficient. But if the correlation is negative, you will get a value lies between -1 and 0 in that Pearson's correlation coefficient. But in some cases, see, here actually we are not in a position to define the type of correlation. Here actually we cannot say that maybe there is no correlation. Specifically, we can say there is no linear correlation. Or in case of correlation 0, Pearson's correlation is 0, don't conclude that there is no relation between the variables. There is no linear correlation or there is no linear relation between variables, because here we are treating only the case of linear. We cannot say that there is no relation between variables. We can conclude that there is no linear relation between the variables. Okay, but anyway, so actually for finding the relationship between variables, we usually start with the scatter plot. But in most of the cases, scatter plot will appear like this. We are not able to reach a conclusion what is the relation between those variables, and even it is limited to only 2 variables. So that itself is one of the biggest limitation. So in that case, we will to move to correlation. Correlation also, it is possible to find the correlation by taking 2 at a time. Of course, all the combinations we can choose, but by taking 2 at a time. So there also it fails because it gives the degree of relationship only. You will get the correlation only as a value. It is not possible to predict or make the future prediction or forecasting using correlation. So that is why we are moving to this type of method known as regression. It is possible to predict. Say, for example, here we have 2 columns, exam score and revision time. So if you are given the revision time, it is possible to predict the exam score using linear regression. Similarly, if you are given exam score, it is possible to predict the revision time of a student using linear regression. And this type of data, that is, if we have only 2 variables such that one will be treated as dependent variable, which we are going to predict. Say, for example, if we want to predict the exam score of a student based on revision time. So since we are going to predict the exam score, we can treat this exam score as dependent variable, and remaining independent variable here, only one independent variable, revision score. So if we have only one independent variable, that we call it as that the regression which we can apply here is simple linear regression. The mathematical form for a simple linear regression is simply all of you have studied in your school classes, y equals mx plus c form, y equals ax plus b, or y equals mx plus c form. Mx plus c, m is the slope, that is coefficient of x is the slope. Here beta 1 is the slope and beta naught is the intercept. I think almost all of you remember these words, slope and intercept. If not, if you forgot all those things, I can just share this slide. Okay, so this one, see this portion actually, this measure is the intercept, and slope is actually given by the difference between rate of change of y with respect to x. That is difference between this y coordinate, this measure divided by this measure. Say, for example, if this is y1 and y2 minus y1 by x2 minus x1. So difference between y coordinates divided by difference between x1. So that measure we call it as slope. So b1 or beta 1 here. Okay. So this is a case of a single variable, single independent variable. But in place of that, if we have more than one independent variable, say for example, look at this example, we have 3 columns. Suppose we are going to predict this yield. Suppose, of course, you are free to predict either time or temperature or yield, it's left to you. But if you assume that, suppose you are going to predict the yield based on time and temperature. So if you are going to predict the yield, of course, yield will be treated as dependent variable. And the remaining, what all variables are there remaining? Here we have remaining 2 variables, time and temperature, that we call it as independent variable. Okay, so since we have more than one independent variable, this model, the type of regression which we applied is multiple linear regression. That is, if we have more than one independent variable, we will move to multiple linear regression. If we have only one independent variable, dependent variable is there, of course. Okay, but take the case of independent variable. If we have only one independent variable, then the model which we fit in regression is linear, simple linear regression. But in case of more than one independent variable, then multiple linear regression. Say, for example, in the previous example, that is case of yield. In the case, if we are going to predict yield based on time and temperature, then this model will be yield equals beta naught plus beta 1 into time plus beta 2 into temperature. Okay, and then here with this example, if we want to predict the simple, or if you want to apply for this to predict the exam score based on revision time using simple linear regression, simply the model will be exam score equals, that is this one. This one, exam score equals beta naught plus beta 1 into revision time. So whatever be the value of revision time, it is possible to predict the exam score, provided ultimate aim here is to find the values of these constants, beta naught, beta 1. Or these constants or estimates. This is actually one of the points which I referred yesterday. In statistics, sometimes we call this beta naught, beta 1 as parameters, but from the computer science or machine learning perspective, please don't use that word parameter, because a lot of other things are there which we use the term parameter. So simply the constants beta naught and beta 1, or estimates beta naught and beta 1, that is enough. Okay, now for estimating beta naught and beta 1, actually we use a statistical method known as principle of least squares. Okay, method of least squares. The method actually says that, see, if we are given two variables, of course, actually we are assuming that the relationship between those two variables are linear. It's only an assumption. We don't know. Okay, by making an assumption only, we are going to proceed with finding this beta naught, beta 1, etc. So since this is an assumption, of course, there will be an error too. So let me add some error e, small letter e. So this becomes y equals beta naught plus beta 1 x plus e. So take these two terms in the left side. Y minus beta naught minus beta 1x equals e. So e, this e. Take the square of e. Okay, so square of e means y minus beta naught minus beta 1x the whole square. Okay, so this term simply indicates, this equation 3 simply indicates sum of squares of error. E is error, right? Okay, take the square of that error. Take the sum of that. Some of those errors. Okay, now the principle of least squares, the method for finding this beta naught, beta 1, that method states that the best values of these beta naught and beta 1 are those for which this term becomes minimum. That is, simply when this becomes minimum, we get the values of beta naught and beta 1. For that, for finding the minimum value of this term, we use the method of calculus. That is, in calculus, actually finding maxima and minima, you all studied in your I think plus 1, plus 2 level in differentiation method, application of differential calculus. A function is said to be minima at a point if the first derivative equal to 0 and second derivative greater than 0. So simply take the first derivative of this equation 3 and equate it to 0. You will get an equation. Since we have two constants here, beta naught and beta 2, beta 1, differentiate this, take the partial derivatives because you have two variables. Okay, differentiate this equation 3 with respect to beta naught, equate it to 0. Differentiate this term with respect to beta 1, equate it to 0. Simplifying those equations, you will get values of beta naught and beta 1. Okay. That is the derivation. I'm not going to the detail of the derivation. So why I suggest, reason is that all these things, especially while doing programming, all these things will lie in a single word linear regression, provided you have imported the module scalar. But we need to know the thing or the concept behind that. What is that? What is linear regression? Actually, beta naught and beta 1, you will get it. I will show you that also. Well, think. Yeah, is it visible? I have opened Jupyter Python notebook. Hope it's visible. Is it visible to the participants?
Yes, ma'am, it's visible.
Okay. Yeah. Okay. So while doing programming, actually, if we import if we use this line from sklearn is sklearn or scikit-learn, SCIKIT. Sklearn, actually, that module is purely for machine learning purpose. Okay, so whatever traditional machine learning algorithms, all the algorithms, we can do it using this sklearn. So from sklearn.linear model, actually, I'm importing linear regression. So once you import this one, and provided if you execute this code, then it is enough to type. Of course, I'll explain these steps, but just to show you. So once you execute that line, then it is enough to use that word for getting all these things. See, here I am getting the coefficient. These are the values of 0.906 for minus 0.0. These are the values of beta naught, beta 1. Is there any differentiation here? No. Is there any equation here? No. Nothing. Only this linear regression term. So that is why, even I know you all are teachers, but teachers also need to know, because students will ask what is the thing behind this. No, so linear regression, actually, the first thing is that we need to know the model. Okay, then how do we get, or how do we get the values beta naught or those constants or estimates in that model? That using the principle of least squares. But of course, we don't need that derivation, but we need to have an idea of that. So that is why. Anyway, I will explain from the beginning. Once I finish that description of algorithm, explanation of algorithm, I'll explain from the beginning. Okay. Yeah. So when this function becomes minimum, of course, in the next step, in the next slide, in the upcoming slides, I'll connect this to the another term. Those who are familiar with machine learning, very much familiar with the term or with the word cost function or loss function. So maybe you might have studied that this particular thing as the cost function or loss function, but actually this is the thing behind this behind this linear regression. Actually, this actually comes from the method of least squares. Okay, and the concept is, when this becomes minimum, of course, cost function becomes minimum. You will get the best model. But best model in the sense, you will get the best values of beta naught and beta 1. Or whatever be the notations. I just use beta naught, beta 1. You are free to use any notation. Okay. Now, yeah. So let me explain with this example. Okay. So effect of time and temperature affect yield, percentage of yield. Look at this. Just I have included it as a case study. So effect of time and effect of temperature and reaction time affects the percentage of yield. I have 3 columns. Develop a model for percentage of yield. Suppose we have to develop a model for regression model. I am going to develop a regression model. I'm not saying that regression is the only model which we can develop from this particular data set. Of course, you can use either decision tree or support vector machine or KNN, etc., etc. Some regression models, because this is a continuous, a numerical quantity or continuous value. So you can apply any of the regression model for this. Okay. So the first one which we are studying here is linear regression. So develop a model for percentage of yield in terms of time and temperature. So we are going to assume that we are going to predict the value of yield based on, that is, if you are given a new value of time and temperature, what will be the value of yield? That's all. Okay. If you are given a new value of time and temperature, what will be the value of yield? Okay. Any issue? Is the slide visible? I think that screen sharing got, right? Is the screen visible?
No, ma'am.
No, madam.
Okay, let me share the screen. I think you can view me, right?
Yes, madam.
Yes, ma'am.
Oh, okay, let me share this. I don't know what happened. Okay. Yeah, what about now?
Yes, it is visible, ma'am.
Okay, thank you. Okay. So the ultimate aim or objective is to simply find the values of these constants or estimates involved in that. Kindly avoid using the word parameters, because that may confuse with but statistically, of course, these things we call it as parameters. But from the computer science or machine learning perspective, maybe this will be a little bit confusing. So use the term estimates or constants. Okay. So this is the example which I was referring. So we have 3 columns: time, temperature, and yield. So if we are going to predict the yield, if assume we are going to predict the yield, or we have to develop a model for yield based on time and temperature. So we have 2 independent variables. The model will be expected yield, or simply yield equals y equals beta naught plus beta 1 into time plus beta 2 into temperature. And our aim is to find the values of beta naught, beta 1, and beta 2. Okay. Yeah. So how do we get these values? I'm going back to our practicals. Okay. See. Okay. First, what we do is that I think all are familiar with the basics of Python. So whenever we import data set in Python, first we need to import pandas. Okay, module import pandas. Then some graphs also, as I mentioned earlier, those who want to do some graphs such as scatter plot or something like that, you can import this matplotlib and seaborn. So why I import seaborn? Seaborn is again matplotlib and seaborn actually used for diagrams and visualization, diagrams and graphs. You can ask me, matplotlib is enough, right? Okay, matplot is enough, matplotlib is enough, but I have imported seaborn also because here actually I have attempted a multiple graphs. So that is why. So anyway, the first 2 lines, seaborn, matplotlib, this matplotlib and seaborn are used for data visualization libraries. Now the 3rd line is actually purely for linear regression. sklearn is the module for machine learning. Then from sklearn, import the library linear model. From that, import the package linear regression. So please, this is case sensitive. So don't leave any space between this linear and regression, or L and R uppercase letters. Okay. Now, as I shared earlier, of course, whatever be the model which you are going to develop, we have to measure or we have to assess the performance of that model. One of the measure to assess the performance of the linear regression is mean square error. Mean square error. Okay. So, of course, even though even suppose you miss this last line, no issue. It is possible to calculate it by using the formula. No issue. Okay, I'll show you that also. Okay. So anyway, at least import at least these packages. Okay. So first for importing data set pandas, then for diagrams and graphs, matplotlib and seaborn. Then for machine learning purpose, this sklearn, from sklearn import linear regression, then metrics. Okay. Now the next line is actually I am importing data set. See the dot read underscore CSV. See, since this is a CSV file, that is why I'm importing. I am using this read underscore CSV. If it is an Excel file, you can use read underscore Excel. And here also, if it is an Excel file, dot XLSX, that extension. Okay. So I have imported the data set. Then see, describe. Yesterday I mentioned this. It is not mandatory to find this describe, but it would be good to find these things. Not only from the perspective of doing some exploratory data analysis. Other than that, if you have some missing value in your data set, by looking at the first column, it's the first row itself, it is possible to verify that. If you have any missing value here, definitely the count will be different under different columns. Okay. And this missing value, checking this missing value can also be done say .info. You can take, you are free to take some information about your data set. From that, if you have not null, means no missing value. Okay. Otherwise, this number will be different, this time temperature. So anyway, it would be good to do this, but otherwise also it's okay. Now, now I am going to fit the model. So before fitting the model, whatever be the dependent variable, keep it like that. Or if you want, you can give a new name for that. But whatever be the independent variables, together give a variable name for that. Here, time and temperature are the independent variables. I have given a name, say X. X is my choice. You are free to give any choice, either letters or words. It's your choice. So anyway, independent variable, please give a variable name to all the independent variables together. Here I have used the ILOC that I think you are familiar with the basics in Python. So to all independent variables together, rename it. Then yield also I have given a name Y. It is not mandatory since this yield Y, this is a combination of uppercase and small lowercase. That is why I have renamed it as Y. So once again, I have imported the data set. After importing pandas, then import the corresponding libraries or packages, Matplotlib and Seaborn for data visualization, then sklearn for machine learning. From sklearn, import linear regression, then from performance metrics, if there is anything, any performance metrics related to that model, corresponding model. Then import, I have imported the data set. So if required, we can find. If required, we can find the describe. Also rename it. This is mandatory to give all together independent variables, rename it. Some way, by some name. Then also I have given another name. Now we are going, okay. This using the Seaborn, my SB actually I have used for this Seaborn. Participant, please mute. Okay, so this is pair plot. Pair plot is nothing, our scattered plot. Only thing is that at a stretch, actually, here I am getting the plot of scatter plot by taking time along x-axis, temperature along y-axis. Time along x-axis, all the combination. Okay, plot of by taking time along x-axis, temperature along y-axis, time along x-axis, yield along y-axis, temperature along x-axis, yield along y-axis. All the combinations you will get by taking a pair plot. See, look at this picture. This picture, don't look at the diagonal pictures, because not diagonal pictures actually. So this picture is obtained by taking time along x-axis and time along y-axis. That is meaningless. No use for that. Same variable along x and y-axis, because 100% relation, 100% correlation between the same variable, right? So don't look at the diagonals, but look at this non-diagonal graphs. Say, look at this graph. This graph is obtained by taking the values of time along y-axis and temperature along x-axis. Similarly, look at this graph. This graph is obtained by taking time along x-axis, yield along y-axis. So similar to that, you will get all the combinations here. This is also not mandatory while attempting linear regression. Choice is left to you. Okay. So scatter plot. Now next thing is correlation. Again, this is also not mandatory. Choice is left to you. But it would be better to do these two things before moving to create or develop a regression model. Okay, correlation. Look at this correlation. See, of course, here also diagonal elements. This one means correlation between time and time. Of course, it is 1. Maximum value of correlation is 1. Definitely, you will. Then correlation between. So don't look at the diagonal elements, because diagonal elements actually relation between the same variable itself. Definitely 100% correlated. Now look at this value minus 0.00756, which is negative, which is the correlation between temperature and time. That means there is negative correlation between temperature and time. Okay, since it is negative. Okay, that is when one variable increases, other variable decreases, or when one variable decreases, other variable increases. Okay, but look at this value 0.8976712, which is the correlation between yield and time, near to 1. Correlation maximum value is 1, minimum value is -1, lies between -1 and 1. So since it is near to 1, which means that there is positive correlation or high degree. It is near to 0.9. So high degree of positive correlation between time and yield. So this will help you maybe in later, especially while treating the case of multicollinearity, all those. Multicollinearity means nothing. See, independent in regression variables, initially we assume we need a prerequisite as time and temperature are independent variables, right? Or some independent, that word itself, it is there. But you have to check from your, that is one of the actually mandatory prerequisites, but no one is checking usually while progressing with regression. We have to check whether the given variables are independent or not. Okay, so that is the case of multicollinearity. Check the multicollinearity. But if not independent, there are methods to make it independent. Don't worry about that. But it would be better to check that. So anyway, even by looking a quick look at this value, these values also, it is possible to find out that. Okay, now next step is actually we are going to develop the model. Okay, nothing. Once you execute this third step, that is, if you import linear regression, simply use that word to develop the model. That is linear regression. See, linear regression. Just I have given a name, my model. That is a name which I have given. You are free to give any name of your own choice. Okay, so once you develop the model, don't forget to fit that model with our data set. So our data set actually, dependent variable, we have denoted it by Y, and independent variables as X, together as X. So this linear regression, actually, I have given a name here as my model. So that name dot fit our data. So my model dot fit bracket X comma Y. X comma Y is the name which I have given to the independent variables and dependent variable. My model is the name which I have given to linear regression. You are free to give anything in the left side. It's your choice. Okay. Now, see, is it possible to get, or is it possible to view the values of beta naught or beta 1 or beta 2 from this linear regression? No. For getting to view the values of beta naught, those coefficients or estimates, .COEF coefficients. Okay. These are the values of beta 1 and beta 2 in the corresponding order itself, as in the data set. Okay, then again we need the value of intercept beta naught. So my model is the name which I have given here. That is why I'm using that name here. Okay, so dot intercept. If you use dot intercept, you will get the values of beta naught, beta naught. So from these values also, again I'm telling you that the model is not there in the Python program. We have to know, we have to write the model. What is the form? Yield equals. So what will be the model here? Yield equals beta naught plus beta 1 into time plus beta 2 into temperature. So yield equals minus 67.88 plus 0.906 into time plus into minus is minus 0.0641 into temperature. Going back to the PPT.
Ma'am, repeat once again the intercept, what the formula that you said to calculate.
I'll show you here.
Okay.
See, this is the general form which I mentioned earlier, right? Okay. So y equals beta naught plus beta 1 x1 plus beta 2 x2. We have only 3 variables here. So here actually the equation will be yield equals, we are going to predict the yield. Yield equals beta naught. Beta naught is the intercept plus beta 1 into time plus beta 2 into temperature. Beta naught is the intercept. Beta 1 and beta 2 are the coefficients. So here actually you will get it like this. Yield equals, you're asking this, right? You were asking this, right?
Yes, ma'am.
Okay,
Yes, ma'am.
So yield equals beta naught plus beta 1 into time plus into, actually we are getting that beta 2 as negative. That is why plus into minus is minus. So that is why we are getting here as minus 0.06. This is beta 2 into temperature. Got it?
Yes, ma'am. Thank you so much.
Okay. Yeah. Now, See, here, this is the model, linear regression model, multiple linear regression, of course, because we have two independent variables, a model which we obtained from this data set, or we have developed the model. Perfect. Okay. Now I am asking you, we don't know whether this model is correct or not, right? We are actually using a set of data. Actual machine learning procedure is that this is the training data set, which we have developed a model using a training data set. We have to use another set of data to test this. Okay. For testing, use another set of data. But for that, we need to check the performance. So anyway, how do we check the performance of a machine learning model? For that, the first thing, actually, there are various methods for checking the performance. These are the things: R-square value, adjusted R-square. Adjusted R-square, actually, we use in case of more independent variables. Then mean square error. So this is the most important thing, mean square error. Last one, root mean square, means just square root of mean square. That's it. So anyway, even you miss whatever be the performance metrics you miss, don't forget to find at least R-square value and mean square error. It is mandatory to find these two things after developing your regression model. Okay, what is this mean square error? Nothing. Simple. You might have studied some formula, all those things, but what is that? See, for this data set, we have developed this model, right? Look at this model. Whatever be the value of, if you, for any value of time and temperature, you will get value of yield, right? Suppose I am going to substitute the values of time and temperature in the actual data. See, this is this time, temperature, yield. These are the first three columns. Serial number, just ignore. So time, temperature, yield. These three columns are actually actual data. See, first substitute time equals 130, temperature equals 190 in this equation. Time 130, temperature 190. So after simplification, you will get a value of yield, right? That value is this one, 36, this one, 36.2185. This 35 is actually actual value given in the question, given in the data set. Okay, predicted value is 36.21, which is obtained by substituting the corresponding values of time and temperature in our model, obtained model. Right? Now, next set, substitute time equals 174, temperature equals 176 in this model. Time, temperature. Simplify, after simplifying, you will get a value of yield, which is the predicted value of yield, that is this one, 76.1024. Okay. Similarly, you can substitute each of these combination in this particular model so that you will get this set of predicted values of yield. Predicted value, we have predicted using the new model. Okay. Now, look at this column, yield. This is actually actual value of yield given in your data set. Okay, now take the difference. Of course, if the actual value is 35, predicted value is 36.2185, definitely by logic we can say the difference between those two values is our error, right? So that take the difference between these two values, 35 minus 36 minus 1.2185. Similarly, find the difference between actual value and predicted value for all rows. See this column, last column. Okay, this column we call it as errors or residuals in regression. Now look at this column. It's a combination of negative and positive, right? Okay, combination of negative and positive. So just to normalize, take the square of all these values. Take the square of all these values. Again, after taking the square, if you have a representative value for all these values, then only you will be able to say whether this is good or bad, right? So after taking the square, find the average of those values. That itself we call it as mean square error. Mean means average. Average of square of errors. Okay, so that is same as the first, or that is the same as one of the performance measure in our regression. Okay, so this, since this is squared value, of course, the minimum value will be 0. Squared value, square cannot be negative. So when the mean square error becomes 0, that will be the 100% perfect model. That you will not, you will never get that. But anyway, So that is why actually you will get some value for mean square error, but our aim is to minimize the mean square error. Minimize means up to 0 only you will be able to minimize that. Okay. So anyway, find the mean square error. I'll show you that in the program. Before that, one more thing, R square value. R square value also is very, see, look at this. This is the one which I mentioned earlier. From the machine learning perspective, the mean square error itself, look at this, predicted minus actual or actual minus predicted, because while taking the square, you will get it as positive. So find the actual difference between these two values. Find the difference between these two values. Take the square, take the average, which is same as our loss function or cost function. Find the difference between predicted and actual. Find the square of that. Find the average of that. Okay. So our aim is to minimize this. So for that, we use a method known as gradient descent. Actually, update the parameters. Parameters, even though I am using the word parameters, actually that beta naught, beta 1, etc. to reduce, so as to reduce the mean square error or so as to reduce the cost function. Okay. Yeah. Yeah. This is actually simple. See, this red line is our fit. That is, red line is obtained by using these predicted values. Okay. So this is predicted, red line. But the other one is actually, the blue points are actual value of yield. Blue points means actual value of yield. Okay. So red line, straight line means actually we are assuming that the relation between these variables are of the form of a straight line. So based on that assumption, we have predicted, we have found out the model, linear regression model, and we have found out the predicted values of yield. Okay, this already I explained. Yeah, what is R square value? R square value actually it is equivalent to the accuracy in classification model. R square value lies between 0 and 1. Say for example, if you are getting R square value as 0.9, 90% accurate. My model is 90% accuracy. Accuracy of my model is 90%. R square value. What is R square? It's simply a degree. There is a formula for R square value. It's closely connected to ANOVA, analysis of variance in statistics. I think some of you are aware of that. 1 minus residual sum of squares by one formula there. 1 minus residual sum by total sum of squares. And it is actually a degree in which how much variations in dependent variable or the variation in dependent variable, how much that variation in dependent variable can be explained by the independent variable. Finding the degree of that. Degree to which the variance or variations, take it as variation in independent variable, can be explained by independent variables. Okay, so that measure we called as R square. Okay, so higher the R square value, more variation is explained by the input variables. Of course, in that case, model will be better. So R square lies between 0 and 1. R square 0 means don't proceed with that model. It indicates a poor fit. But R square 1 means 100%. Usually we take if R square value above 0.5, we can proceed. Okay. Okay, this is simply a graph of it's a bad fit means this points lie away from this line. It's good fit means near to that, but perfect means 100%. It lies in that line. Yeah, this is simply what is R square value, just an explanation. See, expression for R square value is 1 minus residual sum of squares by total sum of squares. Residual sum of squares is sigma yi minus y fitted means nothing. Y means actual value. Y fitted means predicted value. Take the difference between those two values, square, add. That's it. Okay. Then total sum of squares means sigma yi minus y mean. Find the average of all values. Okay. Take the difference between each value and its average. Take the square of that, take the sum of that. You don't have to calculate this, just I am giving you an explanation. But these are the same things which you find in the ANOVA, analysis of variance. Residual sum of squares or treatment sum of squares, then error sum of squares, like that. Okay. Yeah. Now, before moving to the assumption, let me show the practicals. Yeah. Okay. So we are actually standing here. So we have fitted the model, linear regression, then coefficients, then intercept. That, yeah. R square value. Here actually I am finding the R square value. Simply R square value is obtained by dot score. That's all. Simple code. Okay. Here I am getting 0.80. It's good, near to 1. So if you want to round that R square value, here actually I have rounded the R square value and multiplied by 100. So 80.64. The predicted value, by substituting each value of time and temperature, you will get the predicted value of yield. For that, dot predict is the syntax. Okay. Then, yeah, mean square error. So mean square error, simply MSE is the name which I have given. So mean underscore squared underscore. This will work only if you import this last line from scalar and dot matrix, import mean squared error. Okay. So once you import this, once you execute this last line, it is enough to type that same name. Bracket. Mean square error is obtained by considering actual value of yield and predicted value. Predicted value, actually I have given this PRED. Actual value of y, I denoted it by y. That is y, comma PRED. Okay. I am getting it as 1 or 2. See, 1 or 2. Maybe by looking at that 1 or 2, you will conclude, oh, 1 or 2, it's a big value. So my mean square, my model is not good. My mean square value is this much. Don't think it like that. Mean square error purely depends on your data set. Sometimes the value will be, of course, our ultimate objective is to reduce that, minimize that value. But some cases, maybe if you will get mean square value as say 1 lakh or something like that, if your data set is, size of data set is very large, I am not saying that that is bad. You can continue with that. Okay. So for that, for taking the decision or whether to continue or not, always stick on to this R square value. Because no, mean square value, of course, you have to find it, but you may not be able to take a decision that whether that value obtained for mean square is good or not. Okay. Yeah, root mean square also, if you want, you can find the root mean square. But in Python, actually, for finding the square, before finding the square root, we have to import a pack. Not only for square root, if you want to find trigonometric functions or exponential function, logarithmic functions, all those things, you have to import the package known as math, M-A-T-H, math. Okay, see here I am finding the square root. That is why I have imported this math. Then, as I mentioned earlier, without importing this library, then also it is possible to find mean square error simply by taking the difference between y and predicted value, take the square, take the average. Okay, so here actually I have done directly take the difference between, yeah, here. Just error equals, or RES is the name which I have got because other name for error is residuals. So error equals y minus PRED. Y is yield, PRED is the predicted value. Okay, take the square of that. Square means 2. Okay, then dot mean. Okay, in that way also you will get mean square. Okay, just I mentioned that, that's all. But easiest way here, directly you can find if you once you import the package. Okay, yeah. Now the next thing is nothing. Next thing is nothing. Say simply I have made, see here actually I am getting this as array. Okay, I'm getting as array. So if you want to make it as a data frame, just as a column, you can use this dot data frame. My PD is actually pandas dot data frame. PRED, these values actually I'm going to make it as a data frame. The name here I have given is PRED. So PRED, comma, columns equals predicted. Here you are free to give any name of your object, whatever be the title which you want, you can give the same thing here. Okay, see, I'm getting as a column. Those values I'm getting it just to make it as a data frame. Now, if you want to join this particular column with our original data set, simply you can use the code dot join. See, my data is the name which I have given to the original data set, dot join. So here I have joined time, temperature, yield is in the original data set. I have joined the predicted values. Okay. Yeah. And now some more things are there actually in the regression. Just a few words on that. Please don't think that these are the R square value and mean square value are the only things, only measures which we use for linear regression, or for measuring the performance of linear. A lot of things are there. Even regression, statistics actually, usually for those who are doing post-graduation in statistics, one subject itself is there for regression. I think nowadays, some universities offering MSc data science or MTech, there also this paper is there, regression analysis. The things beyond this, or the things which is included beyond these concerned, mean square or R square in regression, there are certain assumptions for regression. Theoretically saying or statistically speaking, you are supposed to do this regression only once it satisfies those assumptions. That is one thing. So let me go back to the slide. See, these are the assumptions, basic assumptions, standard assumptions. Okay. Linearity, that is understood because we are actually nothing to check with that. Okay. Independence of errors or normality of errors, equality of variance of errors. We are getting some errors here, right? We are getting some errors here, right? Just a minute, I'll show you that. Yeah. See, these are the errors. Okay. These errors are independent. No relation between those values. That is one of the. There are methods in statistics for checking independence. Statistical tests are available for checking independence. Okay. You can ask me, or how do we check the independence of these errors? Methods are available. Just I'm sharing you. I know usually while dealing with large or complex data sets, especially from the machine learning perspective, no one will check all these things. But just to improve your accuracy, it would be good if you check all these things. Okay. So one condition is check the independence. Okay. If they are not independent, definitely your model may not be good. One condition. Now, the second condition is these are normally distributed. How do we check the normality? A lot of ways are there. Either you can make a plot, or there are some statistical tests for checking normality, or other methods, the visualization techniques for, I think I have included some visualization, PP plot or QQ plot. See, this we call it as PP normal. This is one of the normality check. PP plot, probability plot. Okay. So by looking at the probability plot, that how do we confirm or how do we make sure that whether that errors follows normal distribution or not? If the values lie along this straight line, that means they are normally distributed. If the values does not lie along the straight line, values, that is, if this blue point lie away from the straight line, they are not normally distributed. So that is similar to PP plot. One other PP plot means probability plot. Similar to that, one other type of test known as QQ plot, quantile plot. Instead of probabilities, if you choose the quantiles, that's all. But there also you will get a shape like this. If that values lie along straight line, you can conclude that follows normal distribution. Then again, methods are there. Some normality tests are there. Shapiro test, Ryan Joyner, Anderson, etc., etc. So while conducting any of these, say for example, Shapiro, all the tests, actually we assume the null hypothesis that data follows normal. We assume the null hypothesis that data follows normal. And finally, you will get a p-value. If the p-value less than 0.05, then we reject null hypothesis. So that means if the p-value is greater than 0.05, then we accept data is normal. See here, actually, I am getting the p-value as 0.38. So for this particular data set, actually, errors follows normal. Okay. So just I am sharing you all these things, but especially if we look or if you want to spend more on that regression, these part actually we call it as regression diagnostics or regression model diagnostics. Lot of things are there. One book is there actually named Montgomery, 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 and with some other authors, Introduction to Linear Regression Analysis. That is a good one to read all those things. So a lot of demonstrations are there in that book. Montgomery, Montgomery, PPT. I think it's there. During the end of the session, I'll show you. Okay. Yeah, anyway, all these things are, yeah, this is plot of residuals versus what is the role of these things. That also I can show you. Yeah. Yeah. Here, just I have used SciPy, SCIPY, Scientific Python, the module Scientific Python. So actual versus predicted, it would be good to plot actual versus predicted, because no, if it gives a shape means if it gives a shape, that means there is a good relation between actual and predicted values. Then here actually predicted versus residual plot. Yeah, this is the one of the point which I showed you. Yeah, what is the need of this? Or I can show you one other in detail. Yeah. Yeah, regression analysis in detail. Same thing, same data I have taken here. Same thing, this part, okay. This part, I'll come to this part, See, please, yesterday, maybe I'm 100% sure that some of you may not agree with me when I explained statistical as well as probabilistic things in machine learning. Some of the participants may, I'm not blaming anyone. Maybe as I am basically a statistics person, that's why I'm explaining all these things. No, I'm not purely a statistics person. I'm standing in both statistics and computer science. But definitely in machine learning, the fundamental concept, all the theoretical concepts comes from statistics. No doubt in that. We all need to agree with that. But computing power, definitely we can't, a statistician can't do anything with that. They need to adopt computational techniques from computer science. Okay, so that is why lot of statistical things in the sense actually for making your model more and more accurate, you have to make a look on all these things. So that is why I am mentioning. Not only for regression, for each of the, for all algorithms, there is something behind that. There are some concepts, theoretical concepts behind that. Okay, since I started with machine learning, regression, just I am explaining that. That's all. Okay, this part I'll explain. I'll come to that. Okay, but before that, whatever I explain, let me show that yeah. See, probability plot. Okay, simply stats dot import stats. Okay, from SciPy import stat. It is better to import this. It will be easy. From the sklearn also it is possible to do, but it will be better to import this from SciPy, Scientific Python, import stats. Okay, then probability plot. Yeah, dot prob plot. That is the only syntax. This part you can skip because for getting the grid or all those things, this part you can skip. First line only is. Okay, so since all the points lie along almost straight line, we can say that it follows normality. Okay, then predicted, this part I explained. Yeah, actual versus fitted also I explained. Yeah, this one, right? Yeah, see, this graph is obtained by taking actually residual versus independent variable. Residual versus independent variable. That is independent variable along x-axis, residuals along y-axis. What is the need of this graph? If there should not be any pattern for this particular graph, if your model is good. Okay, if your model is good, there should not be any specific pattern for this. You will get the points as random while plotting residuals versus independent variable. Similarly, while plotting residuals versus fitted, in that case also, there should not be any shape. If there is any shape like straight line or curvilinear or something like that, your model is not good. Okay, then test also, I have referred some test, right? That also I can show you somewhere it is there. On there. Show you. Yeah, stats dot normal test. Okay, so here actually I am getting the value, p-value. Look at the p-value only. say p-value, I am getting 0.38. In the slide also, I showed you that 0.38. So p-value is greater than 0.05 means data follows normal. Okay, that's good to proceed. Okay, so this is actually only normal test. So it's specifically, if you want to mention Shapiro test or Kolmogorov test or something like that, which I showed in the slide, you can proceed with that. Similar to this, a small difference in the code. Okay, so anyway, these are the things, at least some simple things which I would like to share you. But I'm not saying that this model diagnostic test ends. No, lot of things are there. So as to, if you check all these things one by one, of course, it is possible for you to, especially while getting a good, if you are getting a good accuracy, definitely you will not go for this. But if you are getting less accuracy, definitely you will try how to improve that using different methods. So at least in that case, you can have a look at this. Okay, yeah. Now moving to logistic regression. So before moving to logistic regression, if any doubt in linear regression, you can ask me. Don't wait for the end. Any doubt in either practical side or theoretical side? Linear regression. Yeah, please.
Ma'am, good evening, ma'am. When we are comparing two data set analysis, we are using two sample Anderson Darling test.
Wait.
Okay. In that test, the p-value.
Excuse me, once again, please. When you are using
Anderson. Ma'am, can you hear me?
Yeah, tell me.
Yeah, Anderson Darling test p-value test.
Okay.
Okay. When I am comparing two normalization tools using a higher data set, the p-value become very less.
Okay.
So how can I compare my normalization is right or wrong?
Becomes very less means p-value less than 0.05 or 0.01 significance level. We reject the hypothesis. That means data is not normal.
They show that because this happened because the data set is very large.
Yeah. So one way is you can make it normal, standardize it.
So for standardization, what should I do?
Yeah, simply standardization procedures are there. I think here itself, just if it is here, I'll show you now itself. Just a minute. I don't know, it is there in my, just a minute. Let me check if it is here, I will show you. Standardization techniques are there. Simply theoretically saying each value, it is not here, sorry. Each value minus it, that is, if you do it manually, each value minus its mean divided by standard deviation. That is a basic standardization technique which we all studied, right? So, yes. But for that, simple code is available. You can do it in Python itself, your data set.
Yes, ma'am. When I am doing that test, I get two values, test statistic and p-value, but the p-value is very small, like 0.001. So I cannot compare the original data set and normalize the data set. That's the issue. So I try to normalize.
Yeah, try to normalize it.
Okay, ma'am. Thank you.
Yeah. So any other doubt? Just I'm having a look at the chat also. Is there any doubt? Please feel to ask me. Okay, nothing. Okay, now I am moving to next one, logistic regression. Okay, so participants, if you have any choice, I can take that, because with the limited time, I'm able to explain at least one regression technique and one classification technique. Okay, so let me share the screen.
Ma'am, kindly share your presentation as well as Python code if possible.
Yeah, sure. Sure, I will share with the organizers.
Ma'am, thank you, ma'am.
Yes, yeah. So next is logistic regression. Even though that word regression tail of this word is regression. Please don't think that it is a regression technique. No, it is a classification technique. Okay, that means it is possible to apply logistic regression only if you have some classes or categories. But again, this is again a statistical technique to find the probability of dependent variable. But in supervised learning, actually, it is used to predict the probability of categorical variable. So here, actually, we use a function known as sigmoid function for the prediction. The equation of sigmoid function actually shape is like this: 1 by 1 plus e raised to minus z. Okay, the concept actually, this expression actually, some derivation is there behind this. This actually comes from the term odds. Some of you may remember in your school classes in probability, you study odds probability. So if say we have the probability of girls and probability of boys, then the ratio of these three, we call it as the odds ratio. Okay, take the logarithm of odds ratio, take it as say y, simplify it, you will get this expression. So that is a derivation I can say. See, just by reversing this, say p by 1 minus p, take logarithm, take this is equal to say y. Okay, then cross multiply y or z. Okay, take this expression is equal to z, or this expression log x by 1 minus x is equal to z. Taking exponential on both sides, so the left side becomes e power log. E power log x is x itself. So left side becomes x by 1 minus x, right side e power z, cross multiply, simplifying, you will get this expression. So that is the genesis or origin. This can also be expressed in this form, simply by taking e power minus z outside. Okay, so e power minus is outside, it will come in the numerator as e power z. So this 1 becomes 1 by e power minus z is e power z plus 1. So anyway, either you can proceed with this form or this form, both are same. This itself we call it as sigmoid function. Now, if you substitute any value for z, starting from minus infinity to plus infinity, you will get this function simplified to a value lies between 0 and 1. No doubt in that. Whatever be value, -1, -1.2, 0.1, 1000 or 2000, 1050, anything. If you substitute any value for z, on simplification, you will get this as a sigma of z, sigmoid function as a value lies between 0 and 1. That is why we can say that this is a probability. So finding sigmoid function means finding a probability. Based on that probability, you will reach the conclusion. You will predict whether it is yes or no or whatever it be that. Okay, now what is sigmoid function? Or see, look at this sigmoid function. Actually, the shape of sigmoid function is like this. It lies between 0 and 1. So usually, if you want, you can put a threshold like 0.5. So say for example, if you want to predict whether the new image is the image of an apple or orange, so you can make a threshold as if your value sigmoid function or probability, if you are getting it as 0.5, that belongs to apple category. If it is less than 0.5, that belongs to category orange category, or dogs or cats, or whatever be that. Okay. Otherwise, what we do is that, especially while doing while dealing with the data sets, find a probability corresponding to both probability of getting apple, probability of getting orange, whichever is maximum. That will be the final prediction. Okay, if you want to predict whether it is a dog or cat, find the probability corresponding to dog, find the probability corresponding to cat, whichever is maximum. So that will be the final prediction. So we will proceed like that. Now, one more thing, as I mentioned, this is a classification technique, not a regression technique. Then you can ask me then why that term regression is there. Yes, there is a relation between linear and logistic regression. In this expression, this z is same as our linear regression model. That is, z equals beta naught plus beta 1 x1 plus beta 2 x2 plus etc. But while substituting that beta naught plus beta 1 plus etc. here, on simplification, you will get a value lies between 0 and 1 only, not any value. Okay, so that is the relation between linear regression and logistic regression. So yeah, say one example, say for example, if you want to See whether a car will
മൊത്തം പറഞ്ഞില്ലല്ലോ, ഒന്നുകൂടെ വായിച്ചു പഠിച്ചത്. അതിന്റെ തെറ്റുണ്ട്.
Some teachers are actually teaching her child. I can understand evening time, no worries. Okay, yeah. See, if you are given a data set corresponding to years since, number of years since last service, and here probability of breakdown. If you want to calculate the probability that a car will break down or not based on the number of years since last service. Of course, we know that if we keep pending that service, no, maybe some repair you can expect. Okay, so here actually how do we predict using this logistic regression? See, this is the 0.5. okay, if we make a threshold value here, cutoff value here, probability greater than 0.5 means car will break down. Probability greater than 0.5 means this is increasing, that is number of years since last service, actually it is increasing, right? But probability less than 0.5 means number of years of service is less, right? So car will not break down. Okay, now what about this 0.5? Look at this 0.5. See, corresponding to this 0.5, it cuts the curve here. Corresponding to this, I have some 3.5. Right, 3.5 years. So the threshold value 0.5 indicates that the car is more likely to break down after this threshold value. After this threshold means 3.5 years of usage. This is a real example. Okay. Yeah, another example, that is if you are given the age of a user, income, gender, etc., it is possible to predict whether the user will purchase an item or not. Okay. See, you can ask me, how do we decide user? Definitely. See, senior citizens' choice is different from the middle age or youngsters' choice. So based on the age, income, and gender, definitely we can predict whether an item will be purchased by the user or not using any of the classification model. Logistic regression is one of the options. Then this example also I mentioned, a student teacher. A student will be happy or not based on teachers' some 3 criteria. You can take, say, some delivery of notes or delivery of lecture or something like that. So it is possible to predict. Okay, some other examples. Linear regression and logistic regression, already I mentioned. Linear regression, actually we have a straight line. Logistic regression, we have sigmoid function. And here I have mentioned, so linear regression of course answers how much, but logistic regression, it will happen. Will it happen or not? Here it is used to predict continuous variable. In logistic regression, it is used to predict when it is a category. Outcome is a category. Oh, this is the mathematical part. Yeah, especially while using, so here linear regression, actually 3 types I mentioned: binomial, multinomial, ordinal. So by binomial means if you have only 2 classes, or a binary logistic regression, we call it as binary. If you have only 2 classes, usually that belongs to binary, yes or no, pass or fail. But if you have more than 2, we can approach this one. Okay. Yeah, this is actually a case study. Develop a model to predict the non-payment of overdraft by the customers of a multinational banking institution. So data is given in a logistic file. So 3 factors are given here. I'll show you the program. But before that, just have an idea about simply a data set with a data set. Okay, my model that develop the logistic regression or linear regression. No, I'm not saying like that. Start with a case study or some objective, then try to connect with that. Okay. So the data is given as logistic regression CSV file. So we have to develop a model to predict the non-payment of draft. That is, we have to predict the outcome as paid or not paid, based on these set of variables. First variable or these set of factors. So this actually we call it as explanatory variables. Okay, the last one we call it as target variable, which is the one which we are going to predict. Now, individual expected level of activity score, transaction speed score, peer comparison score in terms of transaction value. These three factors are given. We have to predict whether it is paid or not. Paid is denoted by 1, not paid is denoted by 0 in the data set. And these things also, factors 1, 2, 3, short forms are given in your data set. Okay. Now I am moving to the data set. Okay. Okay. Logistic regression. Yeah. See. Import the logistic regression data. I have imported the logistic regression data set here, but before importing the data set, definitely it is mandatory to import pandas. Pandas used for data manipulation. Now look, just have a look at the other packages. See, all these packages from the second line onwards, it is not mandatory to import in the first line itself. After importing the data set below this line, it's okay, it's fine. Okay, to execute it. Okay, but here, look at the data, look at the libraries or modules which I have used. Pandas for importing data set or for data manipulation. Matplotlib and Seaborn for data visualization, which we use in the linear regression also. The next step also similar to the linear regression, a sklearn.linear model, import logistic regression. Previously in linear regression, we have imported linear regression, right? Now, after that, there actually we have imported mean square error. But here actually, instead of mean square error, we need, it's a classification model. Yesterday, I explained about the different performance metrics for classification model. All those things comes from confusion metrics, then precision, accuracy, recall, etc., etc. So for those things, actually, this last two lines, import confusion metrics and import classification report. And in between, I skipped this line. Don't worry about that. If you want to cross-validate after getting the output, if you want to cross-validate your data set, you are free to import cross this also, this line also. Okay. Now moving to import the data set. Then, yeah, scatter plot. See, there is a difference between the scatter plot for linear regression and logistic regression. In linear regression, actually, we were getting as point. Here it is not like. Why? Don't look at the diagonals. See, look at the scatter plot is obtained by taking. See, this is our data set. That individual expense score, transaction speed score, etc., which I explained in the data set, in the slide. Okay, then outcome was 0 and 1. One was paid, 0 was not paid. Okay, see, scatter plot. How do we plot a scatter plot? Scatter plot by taking two variables at a time. For example, suppose we are going to make a scatter plot by taking this variable, first this individual expense score and transaction speed score. The first point is obtained by taking 6.2 along x-axis and 9.3 along y-axis, right? 6.2 along x-axis, 9.3 along y-axis, you will get a point, right? That point, if it is 1, corresponding to this row, here it is 1. Here actually, see, for different rows, we have 1 and 0. So corresponding to first point, points corresponding to 6.2 and 9.3, it is 1. So that point will be marked as orange color or yellow. I don't know, orange or yellow, which one is pure. Okay, see, if it is 1, mark as orange. If it is 0, mark as blue. For example, suppose you are marking this point, 6.7 along x-axis, 2.7 along y-axis. You will get a point, right? That corresponds to 0. So mark it as blue. Okay. Similarly, take all combination. That is why you are getting blue and red, orange points in this figure. But in linear regression, we don't require this case because in linear regression, actually, we don't have these classes. We have values. Okay. I think you got that scatter plot. So actually, that whatever be that column outcome is the column represents that category. So here you have to represent that column name here. Hue equals outcome. So that you will get it. Okay. So that is a pair plot. Time is going. Okay. Now, similar to the linear regression, define x and y, all the independent variables together denoted by a name, and dependent variable or target variable other name. So here also I have denoted it by x and y, and this is the linear logistic. Develop the model. C equals, don't worry about C. If you skip this C, say suppose I am skipping this. See, this is also correct. Okay. And the role of C, just I have mentioned, give some large value to C. Okay, C equals 1E08 means 1 into 10 raised to 8. That is 8 zeros. Or you can 1E10, 1E11, 1E12, some large value. It's actually a hyperparameter. Okay, just for getting good accuracy, that's all. Okay, but if you skip that C, then also it's okay. You skip C means, but empty bracket you need to put. That is mandatory. Okay, so similar to linear regression, I have developed the model and fit this with our data set. Dot fit. It is similar to the linear regression. But in linear regression, after this step, we have found out the coefficients and intercept. Here also, since there is a relation between linear and logistic regression, we can find coefficients and intercept here also. Okay, I am finding intercept and coefficient. Now, predicted values. See, accuracy also. In linear regression, actually, we have found out R square value. Instead of that, here we have to find accuracy. Accuracy is 97.14. It is good. Okay. Predicted probabilities. That means sigmoid values. Sigmoid function values. If you want, you can do this step. It is not mandatory. But if you skip this predicted probabilities, then also directly dot predict, you will get all the predictions like this arrays. That is all the predictions corresponding. That is what this first, what is the prediction predicted value or predicted outcome corresponding to first row, second row, third row, fourth row, up to 980 rows are here. All these values actually you are getting like this. See, similar to the previous one, if you want to make it as a data frame, you can that pd dot data frame. Okay. Yeah. Cross tab actually you don't cross tab actually dot cross tab is another way for finding confusion matrix, but you can find the confusion matrix directly. Somewhere I have included that. Yeah, see, you can use this step, confusion matrix bracket y is outcome, then that predicted class. Okay, without using that confusion matrix package, it is possible to find the confusion matrix directly by using cross tab. You can use either this way or other way. Okay. Now the remaining things are almost same as the previous one. Linear regression. See, data frame. I have made the data frame. I have joined with that yeah. See, these are the predicted probability. How do we make predictions in linear regression? See, for example, the value corresponding to first row. This is actual value. Okay. The first row predicted value is, the first row predicted value is 1. How do we get that? We are actually finding the probability corresponding to 1 and probability corresponding to 0. Then find the maximum value among that. That is here. Look at this. Look at the first column. Here, this one, predicted value corresponding to 0. This is the predicted value corresponding to 1. Which one is maximum? This one, right? Since this one is maximum in the first row, corresponding to this, we have 1. Say, for example, take another one. Say, look at this. 9.53 E minus 1 means into 10 raised to minus 1. 10 power minus 1. 10 power minus 1 means left side. So, this value is same as 0.95 something. This value is same as 0.04. Which one is maximum? Which one is maximum? This one is maximum. So that corresponds to 0. So anyway, compare these two values. Which one is maximum? So that corresponds to, corresponding class will be the predicted class. Okay. So that is a way. Here actually I have joined all the things, outcome, predicted class, and even probabilities also I have joined. Because now here actually into 10 raised to 10 raised to 10 raised to minus 15 or something like that. I have rounded this to 4 decimal places, and here see. See, for example, look at these values. 0.9904, 0.0096. Which one is larger? This one. This one is larger. This corresponds to predicted is equal 0. So corresponding to this row, the predicted outcome is 0, not 1. Okay. Yeah. Then, confusion matrix, classification report. After importing this one, you will get it precision recall all the things in a single step. Yeah. From this confusion matrix, what will be the argument or what will be the interpretation from this confusion matrix? Actually, this is true positive. Okay. This is true negative. So sum of these 257 plus 695 divided by sum of all values will be the accuracy 97.14. Or misclassified data will be this 14 plus 14. 14 plus 14, 28 misclassified. What do you mean by misclassified? Misclassified means here 28 rows will be there, in which if the outcome is 1, predicted will be 0. Or if the outcome is 0, predicted outcome will be 1. Just opposite to that. Predicted row, 28 rows will be there. Okay. So that is about logistic regression. So time is nearing 9. So you can ask me any doubt. I know with one and even a little bit speed. No, we are not me, whoever be the resource person, able to finish at least 2 algorithms, maximum of 2 algorithms. Usually, be frank, I spent 1 full day for regression itself. That is there. But at least you need to know this much about one classification model I took, then one regression model also. Please, any questions? Any queries? Yes, Sharon raised a hand. Yes. Can you ask me? Yeah, I'll share the notebook. Sure. I'll share with the organizers.
Good evening, ma'am. This is Jyoti Lakshmi.
Yeah.
I have a question. If we have a data set which is of a smaller size, like 50 or 100 rows as records, can we perform these linear regression or logistic regression?
Sure. Of course, you can perform. It is possible to do it, but when your data set becomes higher, definitely you will get more accurate prediction.
Okay. What are the other statistical analysis can we make with a smaller data set? I want to understand
statistical
analysis.
Yeah, the things actually I explained here, all those things are actually statistics. But in addition to that, that is this errors are independent and normally distributed. Check all those assumptions.
Yes.
Then take a plot of residuals along residuals versus independent variables. There should not be any pattern. Then fitted versus independent variable. So similar to those things, there are some other measures also, or some other conditions also. So if you look at detail of regression diagnostics, regression model diagnostics, you will get more about this. So that is why I shared. Actually, it's a course, a subject, 60 hours course. Regression itself.
Thank you, ma'am. Thank you.
Okay, Montgomery, it's a good book. Montgomery, M-O-N-T-G-O-M-E-R. Montgomery.
Good evening, ma'am.
Yeah, please.
Thank you for a wonderful presentation, ma'am.
Welcome.
I have a small doubt.
Yeah.
I am from mechanical background. I don't know. I mean in detail, but
Okay.
I have a small regarding actually one of my some students project. We have taken L27 data.
Mm-hmm.
Simply we ask the ChatGPT to get some code.
Mm-hmm.
Different machine learning tools, random forest, data boost, gradient boosting, linear regression.
Okay.
So to get the regression line, so it was taken only, and to get the best regression line, it was taken only maximum 9 to 10 points only to get the cross diagonal line regression line out of 27 data points. It is right, ma'am, or it is wrong? I don't know.
Out of how many?
27 data points, ma'am. 27 data points.
Yeah.
To get the best regression line, it was
Only
considered
7 data points means that will not give a good model. 7, simply 7 samples.
not seven, around 10
7
data points.
variables or 7 rows.
So if you take a line, some dots are there,
Only
so
7 points.
around 10 points, 10.
No. In that case, I suggest to improve the number of, increase the number of points.
How to improve, ma'am?
You have to increase the size of data.
Okay.
Okay, because now 7 points means that is very, very small.
Yeah. So
Okay, no relevance in that. With
there is
simply
Google
less
Colab,
than
ma'am.
10.
Google
Yes.
Colab. In the Google Colab, you run the code. It was showing out of 27 points, it was showing only 9 data points around that regression
Maybe
line.
the remaining are outliers, I think.
Yes, ma'am. Yes, ma'am. Yeah, outliers maybe.
Yeah, that is why. That's
Yeah.
why I mentioned actually during the yesterday I shared during the pre-processing stage of machine learning, lot of things we need to consider. See the same example. Out of 27 points, you are getting only 7, right? So outlier detection, that is one of the important. You have to deal with lot of techniques are there to deal with these outliers. Okay, so please ask your student to carry out that outlier detection procedures. On the other way, if the student is not aware or not willing to do that, try to collect more data. So that is the only way.
Okay.
Simply 7 points, it is not correct, sir.
Not correct. Okay, ma'am.
Yeah.
Thank you, ma'am.
Ma'am, good evening. It's a great session, ma'am, and you delivered really so well. I want to ask you one thing, that which language is more preferable, Python or R programming, for predicting the models or for making the model?
Machine learning, I suggest Python. But if you are planning to do more statistical things, especially on this regression diagnostic, all those things, no, I suggest to use R.
Okay, can you
But in
just
both,
give
of
me
course,
some differences? What is a basic difference?
basic difference is that,
Yes.
especially if you focus on more statistical things, right? Because now R is actually maintained by a group of statisticians itself. Okay,
right.
So whatever things are there in statistics, it is there, corresponding packages, whatever inventions, it is there. The packages, corresponding packages are
Yes,
available.
just we need to import them and use them.
Correct.
We need not to write the mathematical formulas and
No.
all.
But at the same time, if you focus on some web development activities or something like that, I always suggest Python, because R is not having that capability.
Okay. Is there any dataset limitations also, ma'am? Means the language will give you the result accordingly?
Yeah, now actually, if you are using Google Colab, I think even Jupyter also some 12 GB maximum size or something like that. Maximum 12 GB.
Maximum
But in
12 GB.
Google Colab, actually, if you take that paid version, say with yearly 1,000 rupees or something like that, you can use even more. 12 GB only if you are dealing with images, all those things only, that will go up to that. Otherwise, no, only it will stand below 12 GB. Up to 12 GB, it's free.
Okay. Thank you so much, ma'am. Thank you.
Ma'am?
Yeah.
Ma'am, how to handle imbalanced data, ma'am?
Yeah, imbalanced data, of course, we have to make it balance. Lot of techniques are there with this limited time. Just refer simply, even in Google itself, you can just type how to convert balance to imbalance, imbalance to balanced data. Lot of techniques are available. Okay. But usually, of course, if you are dealing with a large data set, it would be better to use also during the okay. See, imbalanced data, dealing with imbalanced data, then outlier detection, missing data handling, etc. For multicollinearity, that means the data is not independent. So for all, etc. All these things, then if you are dealing with high dimensional data, you can convert into low dimension, especially by using PC, all those things. So for all these things, actually, techniques are there available. Okay. No questions? I think we can, sir, I think we can wind up. Thank you. Thank you, participants, for the patient listening. 2 days. Okay, shall we wind up, sir?
Maula. Mula भी बोलते हैं ना Maula.
Okay. Once again, thank you all. Thank you, dear participants, and thanks to the organizers, FISAT team for the invitation, especially to the principal and management, then organizing department, Department of Computer Science team. Okay. Thank you. Thank you. Thank you all.
Thank you, ma'am.